Pardon? Close enough. Okay. Well, welcome to the Python Epiphanies tutorial that I'll be teaching today. The link to the Jupyter notebooks that I'll be using, as well as some HTML files are there, is at bit.ly/PyCon 2017-Epiphanies. You're welcome to use those notebooks and follow along. There's a single notebook that has the word all in it. That's a compilation of all of the others except the intro, which might make your laptop unhappy because it uses lots of memory. And you're welcome to just look at the HTML as we go along, or just watch the screen and then use whatever other version of Python or means of typing stuff into Python to do exercises or try things out. Contact information is there. You can see here I've quoted from the description in terms of what sort of the not very precise in terms of facts, but maybe emotions in terms of where you might be, or the kind of people I'm really trying to serve well with this tutorial. People who've been using it for a while and maybe have plateaued, and this is to help you get beyond that plateau. I developed this tutorial after teaching other tutorials for a while, and sort of felt like there was this group of people that had been using Python for a while, especially if they'd come from certain other languages and just weren't getting certain stuff. Let's see, about me, I'm a software architect at a couple mutual fund companies in Canada. Most of my time I spend helping quants write Python. They're using pandas and Python and lots of math, some of which I understand. Some of this material is in a Python Epiphanies video at O'Reilly. This is a slightly rearranged and better version of it, I think. I've taught a number of Python workshops, tutorials at previous PyCons and other conferences. This is my 10th anniversary of teaching a tutorial at PyCon. So that's kind of exciting. And then I do coaching at startups as well on the side some. I asked you before we started recording some of these questions, what programming languages did you learn first? And I heard C and C++ and Pascal and Java and JavaScript, and some of you first language was Python. And I think a good mix of people in the room who've used Python from 3 to 8 years, and some of those other languages had used for a number of years as well. So in terms of how this is going to work, the first 5 to 8 minutes is going to feel like a dry, boring lecture, but I want you to try to pay attention because it sort of sets the groundwork for some of the other stuff. And then the first 10 to 15 minutes after that is going to, for some of you, feel really, really slow. Please don't leave yet. It's going to speed up and get better, but I want to sort of dumb things down a little bit for the first while to try to reset the way you think about certain aspects of Python. And I think by doing that, it will help you, even if you already know it in your head, it'll help you sort of get in the right frame of mind to understand Python and how it works and not be confused by it as often. So let me talk about variables. So a variable in math is something that varies, and we are used to this from algebra. Most programming languages, books, courses, culture, really give you, even if this isn't what you learned originally, you sort of absorb this understanding of what variables are in programming languages. Traditionally, the compiler reserves memory for a variable, and it issues type-specific instructions that depend on the type of what's going to be stored in that location in memory. When you make an assignment statement, it actually takes what's in that box and overwrites it with a new value, right? So if there was a 2 there, if I equals 2, and then you say, well, I is now assigned 3, the 3 overwrites. The bits in that box get overwritten with a 3 instead of the 2. Aliases are fairly rare, except maybe as function arguments passed in. Python is sort of on the spectrum of languages. It's toward the side that doesn't do that. It shares the math definition, which is a variable is something whose value varies, but only at a certain level of abstraction. This is unlike the traditional definition. And to avoid baggage, I'm going to use the words name. I'm going to use names and objects and binds and refers to, and I'm going to try most of the time to avoid the use of the word variable, and reserve that for when I'm talking about something that varies in the mathematical sense. So just to show you what what I mean by the compiler reserves memory. Like here, if you take this code and compile it down to machine code, you'll see that these 4 lines here are different. We've got a move-L, and I-mul versus a move-ss, mul-ss, right? And one is because I declared an int, and one is because I declared a float. So the compiler saw the declaration at compile time and said, oh, A is always going to contain a float. I will reserve a box in memory, a location in memory, and the float's going to be there. It might be on the stack, might be on the heap, who knows. Might be static. But basically, when someone does something to that memory location, if they do a multiplication, I have to remember that it's a float because I'm going to issue floating point instructions, the ones with the SS, instead of long integer instructions. So that's what I mean about the types and what the compiler traditionally does. So here's a rough overview of how we're going to do this. I'm going to talk about objects. That's going to be the slow part. And then basically I'm going to talk about names work the whole time. That's going to be the theme that runs throughout the tutorial, is how do we change namespaces, create names, remove names in Python. And then there's lots of stuff following that trail on either side that we're going to pick up and look at that's interesting in other ways too. Lots of examples. Don't expect to catch all of them. I'm going to use introspection and do things that I don't want you to do in code, especially not production code. I probably won't get to the last 2 sections, but you can do those on your own. And interrupt whenever you're ready or whenever you have a question. Some of the questions I'll answer that later, but feel free to ask me those questions. Any questions before we get started with I'm going to show you stuff. Okay, so an object in Python. Everything in Python at runtime is an object, absolutely everything. The creation of object is not related to names at all. Objects don't even know their names, and there are lots of ways to change namespaces. So first, let's just pretend I'm teaching my grade 4 child, which I do 2 years ago, a little bit of Python. Say, my point is I'm going to slow down. Like I said earlier, I'm going to slow down really slow, and it's going to sound like I think you're stupid. I know you're not stupid. You're all very smart, but you may be thinking about this slightly differently. So when I type the 1 at the REPL, the read eval print loop, the interactive prompt, or in this Jupyter notebook, when I enter the 1 and hit shift enter is the way Jupyter works, Python sees the literal, the single character 1, the digit 1. It says, I know what to do with that. That's a literal int. I can turn it into an integer object. So it goes off and creates an object in memory, and that object takes a lot more than 32 or 64 bits. It's a very large object, and somewhere in there is a representation of the number 1. It then takes that object, and because it's being entered at the prompt, it's going to try to output a string representation, a character representation of that object, and so it calls dunder str and gets the character 1 back and prints it out on the output. Okay, I promise I won't do that the whole 3 hours, but that's exactly what happens, and I'm going to do it at least 3 or 4 more times. So I can create a number 1. I can create a floating point number. I can create a string. Each of these, whenever this happens, I'm going off and creating objects. Here, I actually created a 1 object, created a 2 object, created a list object, had the list refer to those things, and then the string representation came back out. So all that's going on every time Python executes a line of code. And I can, of course, do a dictionary. Every object has a single unique ID. All right, so the unique ID of the object that I'm going to create here is that. In CPython, this happens to be, at least currently, a memory address, and that's useful for people who are writing extensions. It's not guaranteed in all versions of Python to be a memory address, and I think in some it's not. What is guaranteed is it's unique. And there's another one, and there's another one. So I can take any of these objects I created before, I can ask Python, what's the unique ID of these things? Every object has some number of attributes. The way you access attributes, of course, is with dot notation. So I can look at that. I get kind of an awkward representation of what it is. It says function str.upper. Interesting, it doesn't say method. We might think about that later. I can call that method, and it will create a new object, right? So a string literal is an object. I'm slowing down again here. It has an attribute called upper. If I ask Python to show me to get that object, and then show me the representation, that's when I get back function str.upper. String literal is an object. If I do the same thing and then call that object, that called object is going to return another object, which is in this case a string object that looks like a string literal. I'm not going to ask how many of you are getting tired of me saying it slow. It will get better. Hang in there. If I look at what all the attributes are of the string object, I get a lot of them. So dir, when you pass it an object, shows you most of or some of the attributes, the main attributes of the object. There's a slightly more complicated definition I'm not going to cover. All the ones that start with the double underscores we call dunder, in case you haven't heard that spoken out loud before. It's a dunder add, dunder class, double underscore. And then there are a bunch of, here are the ones that are sort of the more public facing ones, or at least public and the ones you would usually use, which are capitalized, casefold, a whole bunch of them. Okay, so lots and lots of attributes on this object. Every object has a single type. One way to get at the type of an object, and this is not the recommended way, but you can do this, and we're going to do a lot of this, is go look at the attributes to see how Python keeps track of these things. So what happens here? 3.14, literal is read, a float object is created. It has a dunder class attribute. I dereference it or go find the object that name refers to, and I get back an object. And when Python tries to show me that object via a string, I get back the word float. And we'll come back to that, of course. All right, and there's a string literal. So this is what type it is, right? That's a float, that's an str, that's a list, that's a dict. Same thing. So let's look at the base classes of float. So Python is multiply inheritance, so it has bases, which is the plural of base, because there may be more than one base class. 99% of the time, it's a tuple with a single element. So float 3.14 is an instance of float. Float is a subclass of object. You can look at the method resolution order via an attribute, and you see that float subclass is object. Slightly more interesting one. So when we say 1 equal 1, it's going to create an object. That object is of class bool. Its base class is int, and its base class is object. And its base class, one more, is empty. So we can see that the Boolean that got created there is an instance of bool, subclass int, subclass object. Some objects are created at startup, and they already have names, right? So an example would be the name capital T true. It's got the class. Well, it's the same one we saw before, really. We didn't see the object. We didn't see the string representation of it, but it was there. This should all be straightforward. So you notice that the IDs of those two objects are true. That means they actually are the same object. That's what is means. So in Python, equal means, are these two objects equal? By whatever definition Python or the implementer of the type or class that those objects are an instance of defines equal to mean. Right? So is 3.0 the same as 3? Well, no, they're going to be different objects. Are they equal? Well, that's up to those classes to decide. And so that's what is means. So we saw float before. This is an example of some of the built-in names, right? Float, and there it is there, and there's where the name is, right? So the word, when I access float, when I type float in the interactive prompt, Python looks it up in a namespace, goes and finds the object. When I type 3.14, Python goes off and creates a float object, and then I access its dunder class object, it's going to give me back the same object. And that object, when you try to print it out, when Python tries to show it to you, it's the word float, float. Okay? Okay. Here's an interesting one. What type does a type have? Well, types are of type. So there's float, there's type. So float's type is type. The class of which float is an instance, even though it's a class, is the type. And it's got an MRO, so type is a subclass of object, and it just, you can't get to the end of that chain. It just keeps going. Some built-in functions. There's one, function len. What class is it of? Well, what's it? It's an instance of built-in function or method. Don't worry about what that is exactly, and you'll see that we'll see later that different built-in functions happen to have different, be instances of different classes. It was whatever was convenient for the implementer. Okay, so to review, everything in Python at runtime is an object. It has a value, a type, base classes, a unique ID, and attributes. That's it. That's what defines a Python object. Usually, we can create objects other ways, like we call things. And this section here, I think I meant to put lower. I just added it in recently and missed that. But we'll do this now. So let's do something first before I talk about that, how you usually create them. So let's import the sys module. GetRefCount is a function in the sys module that tells you how many references are there. Give me the reference count for a particular name or an object. It's the object. Okay, it's a question of how many names does that object have. And even the way I said that, how many names does the object have? I'll show you later. That may not be the right way to talk about it. There are multiple names. Well, let's just play with it and see. Okay, so there are 3 names out there in this Python interpreter right now that's running that refer to the object that got created when I did that right there. It's interesting. Why wouldn't there just be one? True, I can understand. There's lots of them. Any guesses on how many nuns are there running right now in the running namespace? Lots, that's right. 25,000, if that's what you said. I didn't hear it clearly. Object is going to be more than none. Actually, it's less, kind of interesting. Okay, so usually we create, often we create objects by calling other things, right? So len is this built-in function. I can ask if it's callable. I'll slow down again. What happens here is len is dereferenced to an object, which is the function, built-in function or method. Callable is dereferenced to another built-in function. A reference to that object that len refers to is passed off to the object that callable refers to, and that function executes and returns a new object, which is, in this case, true. So it's probably not a new object, it's probably the same one, but we can figure that out later if we want to. Okay, so then we actually call it, right? So every one of these is creating a new object, at least to simplify a little bit. Right? That's actually what len will call if it's there. Int's callable. Yep. Dict is callable. Most of the built-in types you can call them with nothing, and they will give you something, sort of the base case back. True is not callable. But bool is. 3.14 has lots of attributes. Those probably look familiar if you remember all of the 40-odd attributes that str had, but there are a few different. And there aren't very many functions, public functions, that aren't dunder functions. And there are a few other ones that have other interesting. I wonder what's going on there. I bet you didn't know that int had all those functions you could access, or attributes. I don't know if those are functions or attributes or something else. They are attributes. Sorry. Of course they're attributes. I don't know if they're functions or non-callables. Okay, so let's keep going. Oh, there's a method wrapper of float object. That's interesting. And it's callable. So let's call it. It expects one argument, got 0. Okay, let's try calling it with, okay. So we can see that's probably how addition is implemented on the float object. That one's not going to work, only because Python uses dot for more than one thing. But I can put parentheses around it and make it work. Oh, that's interesting. So you can't add floats to ints that way. Okay, so I'm going to take a break now. I've got lots of little short exercise sections. When you're doing the exercise, go ahead and type these in, see what you think they do. I'll review them afterwards. Partly it's just for you to think again about the same stuff. Partly it's just to give you a break from me talking. So I'll give you about 2 minutes to do that. I think most of you are done or getting close. So if I get the size of the string A, it's string, by the way, it's not a character. There is no character type in Python. There's only sequences of bytes or sequences of characters. In sequences of characters are called strings. So you would think the letter A, I mean, if we were writing this in C++, how much memory would the string A take? Maybe 2 bytes? This one's taken 50, right? And if I go up to 4 characters, it takes 53. So it looks like there's the sort of the base case, an empty string is probably 49. So there's a lot of memory being consumed, keeping track of what type this object is, what it's a subclass of, all sorts of stuff. Get size of 1, all the way up to 2 to the 30th minus 1 is 28. In Python 3, ints and long ints just magically seamless between them in at least most cases, or maybe all cases, I'm not sure. So you can see that when you start to get large enough numbers, it's going to take more than the 64 bits, and so it adds some more. Okay, so this is just proof that those objects are a lot bigger than they have to be if you were compiling this language. Question? They're all 24. Okay. Implementation detail. I don't know why that would be. I don't know enough about. Are you running 2? Python 2 something? You're running Python 3 as well. What's that? 3.6. Okay. Yep. But again, these are implementation specific, right? It gets compiled to a different architecture. I mean, obviously, if it's 32-bit machine versus 64, you might see a difference. But it depends on lots of things. Okay. So names. Let me talk about names more. I'm still talking about names. So understanding names, you really have to understand how they work. Almost every object is known by one or more names in one or more namespaces. So in the same namespace, you can have 2 names that refer to the same object, or you can have in 2 different namespaces the same name or different names that refer to the same object. Namespaces are like dictionaries, key value pairs, right? Except more specifically, it's name and a reference to the object. That's the key value pair. Names are bound to objects, or they are references to objects. Bound is the term that's used in the Python language spec often. Another way to think about names is it's like a post-it that you put on an object, right? So it's a label, right? Like I've got this laptop, then I put a post-it, I write post-it, or I write laptop, stick it on there. And I say, oh, it's Stuart's laptop. I write that in there, stick it on there, right? Or I've got multiple names. You know, I'm Dad, I'm Stuart, I've got nicknames, etc. Hadley Wickham said about a year ago, and he was talking about R. There are differences in how objects work in R and Python. But he says a name has an object. An object doesn't have a name, and that's a really helpful way to think about it. And here he's showing you visually what's going on, right? Is that that the object doesn't know its own names. The object doesn't have a reference to the names that refer to it. It's a one-way thing. Let's see what the names are in the current namespace. Ooh, okay, I'm running IPython, aren't I? Look at all that stuff. Lots of history, built-ins, lots more input history, I think. Just keeps going, okay, and a bunch of other stuff. Let's clean up this mess and load it. I'm unhappy. What's going on? I don't understand. It worked this morning when I ran it the last time. Okay. Huh. Let me just check because it'll bite me later. Give me half a second. I don't get it. Okay, but I think this is defined by now. There we go. So here's a fake dir that forgets about all the ones that were there before, or remembers not to show me the ones that were there before. I've used that lots of times. Anyway, so if I try to access the name number under, so basically what I'm showing you here is what's in my current namespace. It's like an empty dictionary. There's nothing there. All the stuff that was there I swept somewhere else. So if I try to access number underscore 1, I'm going to get a name error, right? Very similar to a key error, but it's specific. It's a name error in this case. When I do this, what happens? Well, the 300 literal int, the object representing 300 gets created. A reference to it is stored someplace, and the place is stored is in the current namespace, and it's stored as a key value pair, specifically the name and the object and a reference to the object. So number 1 was not a name, is not a name in the namespace. Now it is. I just added number 1 to the namespace and made it refer to an object that I just created, or that Python just created for me. Okay? It's simple, it's obvious, but again, I'm trying to brainwash you to think this way about it. So now if I look and say, what are the names in the current namespace? There's the key value pair. My dir end makes it look like a dictionary, right? So important to understand here is a simple name assignment like this, it's not an operation on the object. In a compiled language, it would be an operation on some memory that got reserved at compile time, or reservable at compile time maybe. And when I say number 1 equals 300, something gets written in memory. And it's related to that object or that variable in a sense. In Python, a simple assignment is a namespace operation. So I'm changing the namespace. Okay? And now if I try to reference it, dereference it specifically, I get back the object. So clearly Python has variables, so we will think about number 1 as a variable. And I'm going to change the variable's value to 400, meaning I'm going to create an object 400. I'm going to change the key value pair and say, oh, okay, in this namespace, the dictionary that's like a namespace, I've got the name 1, I've got the 300. I want you to now change it to be name 1 refers to 400. Okay? Ta-da. So I rebound the name to a different object. I took that post-it off of the 300 and I stuck the same post-it on the 400. Okay? And I see there it is. If I do number 2 equals number 1, I'm saying whatever number 1 refers to right now, please make number underscore 2 refer to the same object. So now these are 2 names for the same object in the current namespace. All right, number 1 is 400, number 2 is 400. And if I look at the current namespace, it shows me number 1 and number 2. Now it shows you the 400 on the right. It's actually the same reference to an object, a single object, which is 400. The IDs are the same, right? Because they are the same object. Number 1 and number 2 are 2 names for the same one. So when I del number 1, that is a namespace operation. I did nothing to the object. Okay? The object, which represents the integer 400, it may still be in memory. I don't know. It really depends on my Python interpreter. At some point, Python may, if that was the last name referring to the 400, it may choose to clean up the 400, get rid of it because it's not used anymore to save memory, right? That's garbage collection. But that's not what del does. Del just changes the dictionary and says, get rid of that key value pair. Okay? And I see dir end still shows the 2, right? Number 1, now I'm back to name error like I was before. Okay? So objects have types, names do not. So a name can be bound to an object of any type. So usually you might read this line right here as, what's the type of number 1? If you want to be more precise, what you're saying is, what's the type of the object that number 1 refers to? Because types are on objects in Python. They're not associated with names, right? And that doesn't work because I forgot to change it. I'm sorry. Oh, no, it's not going to work anyway. Didn't I get rid of both of them? Maybe not. All right, what's the type of number 2? It's an int. Well, to make this consistent, let's this is what I intended. All right, so now number 1. Okay, so number 1 was of type int. Now number 1 is of type str. And it's fine to talk about that way, but remember, it's not, I say number 1, and what I mean is the object that number 1 currently refers to. That's what always should be, you should be aware of in the back of your mind when you're thinking this about Python. Okay? Okay. Object attributes are also like dictionaries. In a sense, the set of attributes of an object also form a namespace, right? So I will be pretty, I will use that quite commonly. I'll talk about the object, the namespace, which is a module object, or the namespace, which is an object. So let's import types, which I can do in newer versions of Python. just to give me a simple namespace instance. And so I've got this object P, name P in my current namespace referring to an object of type simple namespace. All right, I'm getting tired of saying it, so are you. It has a dict, which is empty. If I assign attributes, it's basically doing a namespace operation on the P object, right? P is like a namespace, and it's got those attributes now, and they're stored in the dunder dict. And I can access them with dot as well. So again, those are namespace operations: assignment, access, and deletion. And they're actually implemented via those methods. There's the dictionary. I can access, and you can see that you can just call those methods directly if you want, and they work, right? You don't have to say p.x. You can use p.dundered set adder all the time. How much better is that? All right. So p.deladderx, did that delete? It did delete something. It deleted the attribute, so it deleted the name. It did delete the object. Python may or may not delete the object later. Okay. And similarly, assignment, access, deletions of subscriptions, like list square bracket I, slicings, where it has colon in between, those use set item, del item, and get item, right? So if we have letters is a list of A, B, C, and I can access that, well, that's happening through get item 0, as you can see. Here, I can access there. Either one of those, they're doing the same thing. And here's an example of a slice. This one's a little tricky, because what do you think? Oh, no, this one's not tricky. This one's pretty straightforward. This one's maybe a little bit tricky, right? So letters starting at 1 and going as far as you can, change what was there, Bravo, to now be Bravo Charlie. And so it did that. And you could do the same thing like this, right? So you notice I have slice. I'm actually using the built-in name slice to create a slice object. Python did that for me here. It created a slice object. Here I'm doing it explicitly, which is handy occasionally. And you notice I had to put in the none. And why did I have to? Well, it's because slice actually has a signature, which is if you pass it 1 argument, it's the stop. If you pass it 2 arguments, it's the start and the stop. So that's why I had to pass it the none up there. If I didn't pass it the none, then I would get slightly different behavior. So I said use equal for equality, double equal. Don't use is. If you weren't listening to me then, maybe you'll listen to me now. All right, different behavior. Why is it doing that? Well, the right answer, and I'll say this a few times in this tutorial, is you shouldn't, it's not your problem. It's not something you should care about. Why is Python doing that? As long as you obey the contract Python has made with you, there will be no problem. If you want to know if they are the same object, use is. Usually you don't care. In this case, all I want to know is, well, I don't know what you want to do. This is a toy example. But the point is, if you want to know that S and T have the same value, use double equal. If you use is, thinking it will give you double equal, sometimes it will, sometimes it won't. And why? That's because the implementers have optimized certain things. In this case, it has to, well, I explained why down there. It has to do with identifiers. Here's another example. Right? So Python implementers can do what they want. They have said to you, here's how is works. Here's how double equal works. Use them the way we told you, and everything is fine. If you assume more, if you assume that they would implement it a certain way, which would be slower, then you may run into trouble. And here's an explanation of why that happens. I mean, the string one has to do with identifiers, and the integer one, I kept saying, I created the integer 300, I created this, I created that. Well, it turns out Python pre-creates some of these things. I mean, we can actually see what they are, like this. If you look at those CPython memory addresses, you see that from from -5 up to 256, and you can check all the ones in between and both ends if you want. They're at a different area of memory than the rest of them, right? So when I ran this code, the numbers from -5 through 256, it went and said, oh, you want a 255? And it said, wait, I've got one already. Use this one. So it doesn't recreate all those relatively small numbers. And that's just to save memory. Might save speed too. I think it would. No, it probably does. Yeah, of course, because creating one that already exists. It's a trade-off. Some other examples. Right? Even if you do stuff on the same, well, again, I did it as one line here, but with semicolons, which you don't usually see in Python, but you can put multiple statements on a single line with a semicolon. It's pretty rare. I equals j equals 500. This is syntax that says make I and j both refer to whatever's on the right. If you want to see why this is happening, you can go disassemble those two, and you can see that it compiled them into different sets of byte codes, right? And that's completely legit. There's no test case that breaks because of that. At least no legitimate test case. Okay, so I've got a few more exercises for you in the ref count area as well. So I'll give you a good 3 minutes if you want to do that one. Yes. Do I know why there are no symbols in Python like in other languages, in the sense that there's an attribute of the object that's the same as the ID? The name of the object is its ID? Yep. Yeah, I'm not sure I understand the question. Let's talk about it at the break. Or if I haven't answered it elsewhere as we keep going. But it sounds like an interesting question once I get it. Okay, so let's just look at these. So why are you supposed, so sys get ref count 1, I understand there's lots of int1 objects out there. It's fair number 20s, lots of objects, a lot of nuns like we saw earlier. Why are there 3 of the number 1, 2, 3, 4, 5? Did it exist, do you think it existed in Python before I made it exist there? I suspect not. So what ref counts are there? Let's, how about this one? So here, Sentinel equals object. So if you call object with no parameters, it just creates a top level, an instance of the top level class, which is object. And when I call ref count on it, there are 2. What are the 2 references to that object? What's that? No. And I'm not saying that because I've read the C. I'm just inferring. It can't be that, because I know what the 2 are, and it's not that. That would be 3. Yes, that's one of them. And the other? Yeah, the name right there. So there are the 2 names that exist. Let me rephrase that. The 2 names that existed in some namespaces when this integer object 2 was computed, one was this name Sentinel right here, and the other was getRefCount takes a parameter, and when that argument was passed to getRefCount, there was a name inside getRefCount, and that name referred to the same object. So that was the number 2. Those are the 2 references to that one. And now there's just the one. Some of you may not get the reference to Sentinel, but sometimes you'd like to have, let's put a -1 at the end of the stream, and that way we know we're done with the file or something like that. Well, that always gets you in trouble. Well, if you're doing it in memory, you don't need to pick a value that might be some other value. You can just create one. So there's the Sentinel object. Create the Sentinel object. It's never going to be equal to any other object. Okay? Okay. Let me get rid of all of these and bring up a trusted notebook. I think that's what went wrong with the Derpy. There's a newer version of Jupyter, and it has the issue of issues with trust, and that's I think what was going on. But where am I here? Okay. So before I forget, let me remind you that I am going to forget when the break is or should be. We go from 1:20 till 2:50 about for the first 90 minutes. What's that? Oh, at 3, so it's not exactly in half. Okay, so if I'm getting close to that and it looks like a good stopping point, especially if you're itching to go, then remind me, isn't it a good time for a break? Especially if you want to get ahead of the crowds, I'm happy to stop a little bit before. So we'll break for about 20 minutes somewhere in there, 10 or 15, we'll see. I'll tell you before you go. Any questions before we keep going? Okay, functions. So the definition of function adds its name to the namespace. So this is one of the things that changes the namespace, is the def keyword, right? All right, so I just added how many names to the current namespace? 1, and that's the name add, right? Now, interesting, when I look at the representation of this function, there's the word AD. Those letters ADD are in there too. So there's 3 characters ADD in the current namespace, and they're also, here's an example where I said objects don't know their names. Well, here's maybe a counterexample where this object seems to know something about its name. You could say at a high level it knows its name, and there it is. Earlier versions of Python, you might not see qual name. But it's not a name that's guaranteed to be its only name or its primary name. It's the name it was made with, and it was helpful. And the reason it's added there is because it's useful to have that for error messages, for example. Okay, let's change its name to multiply. So if I now try to access multiply, will I get a name error or not? You don't have to shout it out. Actually, mostly I want you to think about this. Like if there's some keener in the crowd who always shouts the answer right away, I'm going to stay quiet because I want you to think about it. When I ask the question, it's rhetorical. Think about it. Am I going to get a name error here or not? Does the name multiply exist in the current namespace? No, it does not. And I get the name error. All right? Even though the add name refers to the object, which is the function add that I defined, and it thinks its name is multiply, it doesn't mean that I can access that name. Right? And if I look at add earlier, when I looked at add, I got function dundermain.add. Here I have function dundermain.multiply. I could do this, and now multiply will work. As in, there's a name for it, right? So it's just an object and has some functionality. It thinks its name is multiply because I told it to forget about the word add. Okay. How many of you knew already that functions had dictionaries? How many of you ever used it for a legitimate purpose. It's kind of interesting. I mean, there are times when it's useful, but you can just do things with them if you want. So function definition defines a new namespace, adds parameter. So function execution, sorry, let me slow down, defines a new namespace. So when I call the function, when the function is executing, there is a namespace inside the function, and it knows the names A and B and plus maybe others. All right. So here you will see, all right, A and B, those names existed for a little while and then they went away. Okay. Default arguments. Assume you're aware of this. Right? So default arguments, the default value you give to an argument is evaluated at when the function is defined, not when the function is called. Okay? And that's one of those cases where it gets you in trouble if you use square brackets, for example. Give me an empty list, and then you modify it in the function, and the next time you call the function, it's not empty anymore because it only gets evaluated once. Yeah, I should make that explicit. That's not very explicit. Yeah, it is. Yeah, it's, again, well, I think the first one's pretty explicit. That's when it got evaluated, neither of those times. I don't think that's worth it. Okay, so let's try this one. Oh. Now that may not be, the other one I think everyone knew, or most of you knew. This one you may not have known, although it does make sense if you think about it. It has to be this way, right? So it's only when I call F1 that F2 really gets defined and its default argument called, or at least the second part of what I said, that its default argument values are evaluated. Those expressions, right? So every time you call F1, at least this part is getting executed. I'm saying at least because I haven't gone to dig into the code to see if there's some optimization where it pre-compiles parts of it. I don't know. Function annotations. Anybody here using function annotations yet? And for typing or something else? Oh, yeah. You tried F2. Tried what? I'll get to that. It shouldn't have worked. So that's good that it didn't work. So function annotations, in case you're curious, they're just arbitrary expressions, right? So you could have, obviously this works, and it's what you might expect if you're using function annotations for typing, or for, whereas here you can clearly see that those annotations, I can do things like type int 99, like they don't have to be types, they can be any expression, it gets evaluated at that time. I should put a print in there to make that more clear when it's evaluated. So try a few things with functions. I'll give you another 3 or 4 minutes. And I'll wander around for questions if you have them. Okay. So here I'm just defining a simple function, or you did in your exercises, if you got to it, that shows you what's being passed in. That one should be fairly obvious, right? So the arguments get passed in. Star args and star, well, args is often the name given here, but you can choose whatever name you want. And the star collect any remaining regular or default keyword, regular or keyword arguments. And you can see here, so here's the A and the B show up in the keyword args dictionary. Let's create a tuple. Just to remind you, there's a dictionary. Just to remind you, if you pass a dictionary to a list or consume it as an iterable, it just iterates over the keys, not the values. So here, if I just pass T the tuple, it shows up as a single argument, which is the tuple that gets passed to it. And here is a, by the way, I'm doing surveys as I teach this in various places. How many of you pronounce it tuple? Raise your hand. How many of you pronounce it tuple? Oh, okay, interesting. I think it might be a Canadian-US thing, partly. Not entirely. Eh? What's that? It's a Thursday, so I pronounce it tuple. I do some of both. I'm confused. Okay, so here you can see, right, FT, it goes as one argument. Here it actually unpacks it into two arguments. And this one, what's that going to do? Sorry. It's got to be a mapping. And there you can do. So, any questions? Okay, scopes and search order. So we've looked at assignment. We looked at del, which is a namespace operation. We looked at def. And I forgot to mention def. Part of I sort of hinted at it, but the name add, when Python reads the add, it takes that string and puts it in two places. It puts it in the namespace and it puts it in the function object. Def name, so adds it. Lambdas do too. And then when you execute the function, the arguments, the parameters that are defined in the signature become names in the body while it's executing. And then the resetting. All right, namespace is a mapping from names to object. It's like a dictionary. Namespace operations. Scope is a section of Python code where namespace is directly accessible by using a name. For indirectly accessible namespaces, that should be an S there, I think. No, for an indirectly accessible namespace, you access values via dot notation, right? And we've seen that. And here's the part I really want you to look at. Here's the namespace search order. First, it starts in the local names, the innermost scope local names. What does that mean? Well, it depends. If you're inside a function that's inside a function, when that function is executing, it looks first in that function's body, and then it goes out. The names of enclosing function, and then it goes out. Search starting with the nearest enclosing scope, and then it keeps going until it gets up to the module level outside of any functions. Middle scope contains the current module's global names, and the outermost scope is built-in names. Okay? All namespace changes happen in the local scope. That's really important. And we'll see an example of that. So don't reassign built-in names, right? Len is a built-in, therefore you should never call your own variable or your own name. You should never, I said the word variable. You should never call your own variables len because someone's going to get confused and think it's the built-in. There's nothing stopping you from doing it though, so let's do it and see what happens, just to make sure we understand how names do work. All right, so let's do this. All right, so def f print line a. Okay, looks good. So I've in that function, I'm going to call that function, and in there I'm going to print line a and shows me the built-in function len. Right? So you can see what's going on there if I scroll back up, right? It's looking in the, so as it's executing this, it sees the len, doesn't find it in the local namespace, goes to the next enclosing scope. Oh, we're not in the function anymore, we're at the module scope, and it finds it there, somehow, there or above. I'm going to be vague for a moment. Well, okay, I won't be vague. It actually finds it in namespace containing built-in names is where it got it from. But before it looked there, it looked in the module's global names. Okay, back down here. So let's define len as a function inside the function f. So now when I call f, and I define, inside f I define the function len, which does nothing. By the way, why does Python have a pass keyword? Does C++ have a pass keyword? Why does Python need one? What's that? Exactly. In case you were wondering, that's why Python has a pass, is because if I leave the pass out and just put a comment, it'll say, I don't know what to do. There's no body here because it's all about white space for indentation. Anyway, so then I print len. So when this len here, it's going to go look in the current namespace and find this name that got defined just beforehand. And it prints it out, which you saw right there. And its name is kind of cool, a function f.locals.len. All right, what happens here? F.len, right? Pretty similar, right? I'm going to find the function. I'm actually going to call the function, and in the function that they called, right? So I'm going to call, when I call f, it's going to define len. It's then going to call len, which is going to print something, and then it's also going to print it down here. So let's see what that does. F. So line B gets called, and so in here, the len it finds is this function, and here the len it found was this function, and here the len it found was this function. So all the same local name at the same address. Okay. And how about this? It's gonna be same. Very similar. There it is. So it finds that one. So it finds that one. Sorry. Okay, so let's now add a little more complexity. Let's put a local name inside the function len. So I've got a built-in, I've got the function f, I've got len as a function inside it, and inside that function I've got a local called len. All right, I'm just exercising your namespace muscles here, making sure I'll just give you a chance to practice how does it actually work. So when I call f, the first thing it will do is define this function, but I won't see any activity because it's not executing it. Then it's going to print, I think it'll print that function. Then it's going to call that function, and then it's going to print that name. Well, the contents of that name, as in, see, contents, there's a variable way of thinking, the object to which that name refers. There we go. Okay, of course, back outside, does this name leak into the enclosing namespace? No. Does this name leak into the enclosing namespace? No. That would be a bad thing. If it did, then every time I import a function and someone else used a name that I used, it'd be a mess. That's answering your question. That when you've defined this function here, it's in the enclosing namespace is where that name exists, or that version of the name, let's say. Okay. So now back out here, no problem. Function len. So you can do this if you want, and it works. And then you can do print len, and it says, sorry, I can't call the integer 99 like it's a callable, is what it says there. Int object is not a callable, right? And that's because I overrode it. All right, so what will this do? Will it delete the built-in len function? No, it just uncovers it, right? And now when I call the same print len, I haven't changed the definition here, right? Here I defined it, here I called it and it failed. Here I'm going to call it and it's going to succeed. Because when it goes looking for the function, the name, it looks first locals, then out, right? And it finds the right one. Okay, pass. Yep, you can just do that. Let's try pass equal 3. Can't do that. Len is not a keyword. Pass is a keyword. And it won't let you do it either. In case you're curious, here they all are. And by the way, keywords are the only identifiers. I said everything in Python's an object. Keywords that you see, they're not exactly objects. They influence the compilation, but I don't think they're exactly objects. I mean, unless you're doing eval runtime, at runtime. Okay, so any questions before we move on? Yes? If I what? Del len again? So up here, Yeah, so right here, for example. So len currently is the function that's built in. Oh, wait, is that the right one? Oh, I think so. And if I try del len, interesting, eh? Did you know that? Okay. I think I've seen that, but I've forgotten it. It's not defined, but it is defined. Oh, it's not defined. Well, if it's not defined, then it's lying to me. It said it's not defined. So interesting that this name is a little bit misleading, right? It's not defined in the current namespace. It's not defined in the global namespace of this module. But there's sort of the fallback, which is the built-ins. He asked me to del len again. So up here, I said len equals 99 up above, then I del len, which took the name len out of the current namespace, and now it can see the built-in one here at line 56. And if I do it again, it says, instead of trying to delete the built-in and failing, it doesn't even try. It just says, sorry, there is no len defined, which is clearly not true at some level, because when I try to use it, it goes to the built-ins and gets it. Okay, yeah. To do what from built-ins? I hope not. I don't know. I don't know. Oh, interesting. And you did that through the Dunder built-ins, not as opposed to there's also a built-ins module, and don't remember the exact relationships. So, good way to crash an IPython console. Try to del space dunder built-ins dot len. Yes. Anybody remember the answer? Remember the answer from a few minutes ago? Exactly. And the reason I'm not saying shame on you for forgetting. I'm saying that actually governs it all, but it doesn't. And my point is, remember this rule, and then you can answer questions like that. Is that we skim past it, and it's like, oh yeah, whatever. But that question helps us realize, oh yeah, if you really get that rule and remember it, then it makes sense. All namespace changes happen in the local scope. So that right there answers the question, and that's the one to remember. Okay, then a bunch of stuff just falls out from that. So. You mean like del space p dot x? It calls p's dunder del method. And don't ask me the next question, which is what does that do? I mean, what it does is if you've overridden it, it might do something. And then after that, I don't know exactly how it works. Somewhere hidden in the internals. Okay, there are the keywords. Okay, so let's do some fun here. Test outer scope. All right, so if I call test outer scope, I can see that the X, it gets to it, finds it no problem. And if I test local, let's define a local, which has, and give it, make that name refer to the object 2. And I can see that X in the local scope of the interpreter, which is the module scope under main, is 1. But when I call test local, I'm going to see the value 2 that got assigned to the local X up there. All right, and we can see that X is still 1. And now I define test unbound local. It's going to print X and then assign X. So when it prints X, which X is it going to find? Well, let's find out. You think it'll find the 1, or will it find is there any way for it to find the 3? It's a hard question to think about. It's so hard to think about that Python can't even think about it. And this is where you get the unbound local error. Right? So this is the closest thing you might see in Python to an uninitialized variable. Local X referenced before assignment. Local X referenced before assignment. So it was trying to access the local X. Right? So where did it get a local X? And the answer is, well, let's just make sure X is the same. The answer is hidden in here. So test unbound local is a function. It has a dunder code object. And that dunder code object has a bunch of attributes. It has the number of positional arguments. It has the name of the function. It has the number of locals, which is 1. Even before I execute it, it knows that it has a local. Okay? And it even knows the name of it. So when it compiles the function and creates the function object, it sees that there is an assignment. And it knows from that rule up above, it's a namespace operation. It happens in the local scope. Ah, there's the local x in this function. So let me put one in my compiled object information. And then when it sees the print of the x, it goes, oh, yeah, that's the local. Let me go get it. And it tries to get it, and there's nothing there. Right? So that's what's going on here. And there's more there if you want to look at it. And if you really want to look, let's go. Let's go disassemble some more code. All right. So here's the load fast, and here's the store fast. So the load fast, the store fast says x equal 1, or whatever the assignment was. The load fast says go get that fast local. It's called fast because there are things called fast locals. It's going to go to that local variable, that local name, and try to get it, but it can't because it's not initialized yet. It doesn't have a value. Okay? So that's why unbound local errors, that's what they mean. Right? So again, just to reiterate, what happens is when it compiles the function, like when it sees, by the time it's compiled, it's got a bunch of bytecode that you saw down below. And so when, and it figured out that there's a local. So the print x got evaluated by the Python interpreter, or compiled into bytecodes that say access the local variable x. But the local name x doesn't refer to anything until after the next line. Okay? So it kind of fits with the way local names work. Could we change Python's behavior to do something more sophisticated here? Yeah, but it's, there's a lot of, throughout this tutorial today, there are a few places where I'll show these what people call warts, these little edge cases. Python is very good, in my opinion, at choosing to leave or even design in warts that makes other parts of the language so much simpler and so much more powerful. And so if I show you these things, it's not to say, oh, look, Python's broken. It's no, they're design choices that were made that make Python a great language, and some of them leave these little edges where they kind of confuse you sometimes. Well, if you understand why, my hope is then they won't bother you so much, if they bother you at all. They bother me sometimes, like, what's going on there? Okay, and then there's the explanation from the FAQ that tells you exactly the same answer. I'll let you read it on your own. If you want to look a little further, you can, after the tutorial, compare those two. If you do a equals b, b equals 7 versus b equals 7, a equals b, and you'll get similar kind of thing, just to, if that interests you and you want to cement it. All right, let's look at global. All right, test global. What does that do? So you can put the global keyword in front of a name inside a function, and it tells the Python interpreter when it's compiling the function into bytecodes to treat the x differently, right? So in this case, I check what is x, and now when I call test global, it's going to try to print bx, and then x equal 4 happens. Is this x equal 4 a local namespace operation? No. And if you answered yes, you were thinking the right way, but it's because I didn't tell you that global overrides that. That's exactly what global does. It overrides that rule and says, okay, I know what the rule is, but in this case, I want this one to actually, don't create me a local. So when you see a reference to it, go up the stack, the enclosing scopes to be more precise, more accurate. This one? Oh, this one? I said you could look at this one later. Okay, I'll look at it at the break with you if you want. Sorry. Good catch. Okay, so when we call test global, then it's going to print b1, which is what the global value was way up. Oh, it's way up there. Sorry, I should have reminded you what it was. And then it's going to assign x to 4 and print c4. And now what happens if I look at x? Is it going to be 1 or 4? You can get this answer right. What did global say? Don't make a local. Therefore, it's the x that was outside. So the X that is outside is going to have the 4. That's what global means. It says don't do the local name at all. Yes? Try it. Yeah, try it. Go for it. Try it. See what happens. All right, so he's saying let's trade those around and see what happens. I encourage you to experiment. I'm going to apologize to the people I'm not going down those rabbit trails. They're really interesting ones, and that's how I got to teach this, was by going down those rabbit trails lots. But I want to keep going to cover other stuff. If I do that too much, Ray, hey, go ahead, speak up. Okay, so here if we look at test global, it has no locals. And if I disassemble it, it doesn't have a load local, load fast, it has a load global. So different kind of code getting compiled there. Because that's what global means. It says change your rules when you compile this function. Okay, so Python 3 added a non-local. So that's for you to do. I'll give you a few minutes. Okay, let's keep going here. Let me back up first and just make it a good question, which is like when you say global, a couple things. One is I said I may have misspoken and said that the global X means turn off the local name logic in the compiler. It does that, but it does something more explicit. It says anytime you see X inside this function, refer to the global X, not just one that's not local, because that's what non-local does, right? So then so here, this X and this X and this X all are referring to the X that is in the global namespace further out. Okay, so that's why it does what it does. This function on locals one, that one I think should be, any surprises there? Those of you who did it, made sense, right? So it's not as strong as global, which says don't use this one, use that one. It's saying, well, no, just do more what I misspoke, how I misspoke and said don't do the locals, just go look elsewhere. And another an interesting question would be, you could put in more layers there and play with it to confirm that it works the way you think it does. My understanding, and I'm 95% confident I'm right, but I haven't actually gone to read the document to see, but I think it will go looking as far as it needs to. So I think non-local and global will often have the same behavior, depending on what code you've written, right? That it's going to go up and find the global. I'm pretty sure it does. Yep, it'll look in the enclosing scope, So we're function F3, which was written inside F2, which was written inside F1, which was written inside a module, and built-ins presumably as well. It does exclude global. Ah, good to know. Okay, that sounds vaguely familiar. So it does not go to globals. That's kind of surprising. I wonder why that choice was made. It surprises me. It's not intuitive. You don't want to be surprised by language design in large ways. The sign of a good language or good code, I think, is when you're not surprised. The fewer surprised, the better. Okay. And then there's some more stuff you can go look at. Let's poke around slightly at the built-ins. Lots of built-ins that there is. So let me just, I'm just skim through this quick, and the code here doesn't matter. I'm curious, what are the built-ins? And the answer is there are 143 of them, of which 76 of them are not exceptions. And I can go look at those exceptions if I want. There they all are. And you can also just go look in the documentation. So here are all the exceptions in Python. This one, by the way, NB, nota bene, this is the top level you should ever use, right? So a bare except statement is not a good idea. If you want to catch every single exception there is, stop at this one. And that's why almost everything is a subclass of exception. The base exception has system exit, keyboard interrupt, generator exit. Well, those ones you should not ever catch. And then there's lots of other ones. But if you're still using Python 2 or recently moved to Python 3, there's a lot more. This is a much richer hierarchy in Python 3 than it was in Python 2, which is nice. So what about all the things that aren't? They're all the ones that aren't exceptions. Some of those will look familiar and some maybe not. Here's what I told you about. Use exception, except exception is the right way to do it. Not like you could, in theory, you could just delete from here all the way to the colon, and Python will let you do that. Don't. Just advice. There we go. So notice this name. I just created that name, right? So that is a name. So that again, there's the main namespace operations like def and assignment. There's little edge cases like inside a for loop, etc. Well, here's one where you actually can create, this name gets created for this block of code here. Okay, so these two types cover a whole bunch. So type, here are all the ones that are type, and here are all the ones that are built-in function or method. It's kind of interesting, but not really helpful. because there's stuff in the top list that looks to me like it's more like a function or a method. And there's stuff in the bottom list that looks to me like, is that true? Is there anything in the bottom list that looks more like a type? Maybe, maybe not. But again, this doesn't matter. I don't care what it is. I care how it acts, right? If it walks like a duck and quacks like a duck, it's a duck. And that's the way you should write your code as well, is think about, what do I need to know about this object I'm being passed? As opposed to, oh, it's a list, I can do this. Well, no, just think, what's the minimum I need to know about it? You write your code to handle that minimum, then your code can be extended to do things you hadn't expected in good ways. So don't assume you're being passed a list. Just assume you're being passed something you can iterate over, for example. Anyway, and then there are a few leftovers in case you're curious, which are these ones: not implemented type, none type. Interesting that those aren't exceptions. Ellipses. Anyway, doesn't matter. This was just sort of for fun. So let me let's leave it because I may not have saved it for my corrections. Okay. I did this. No, I haven't done this one already. Okay, so we're at section 3. Sorry, I got lost for a second there. Any questions before we keep going? And how are we doing for time? So breaks in 15 minutes. Is that right? 3 o'clock? So I'll try to let you go a couple minutes early. Cool. So we've seen these things so far. There is a function called locals and a function called globals. And those are the sort of the things that, other than things that start with underscore, in the globals and the locals. And often, like at the top level of a module, those are going to be the same. So if you ever see code like this, just shake your head and say, what were they thinking? Right, so x equals 0, locals x. So I can get, it's basically giving me a copy of the namespace as a dictionary kind of, and I can actually do that. Don't do that, right? But they are there, those two functions, locals and globals, and occasionally come in handy. I used to use them in non-production code when I was trying to do what fstring now does really well, which is great. And if you think you should use them, beware, it won't always work the way you expect, right? So even though I said this is like a copy of the locals namespace, and so I can do this assignment, but then I look at it, it's not 5, it's still 1. And that has to do with fast locals and how it optimizes stuff. Okay, so we've covered a whole bunch of stuff. Let's look at import. Uh-oh, is this going to fail on me again? Or was I just... I think it was trusted or I was sloppy. Okay, so nothing in my current namespace. Again, I'm using underscore dir just because the regular dir is going to show me lots of IPython and Jupyter, IPython mess, lots of variables. So I'm cleaning it up here. If you're using just the interactive prompt without IPython, you can just use the regular dir and you'll get pretty similar. So import CSV. Now I've got the CSV module there. It's added a new name to my current namespace, right? And I can look at that, and it tells me, oh, it's a module CSV. Oh, and now you know I'm running Windows. Look at that. And I look at the contents of that module, or the attributes of that module, or the contents of that namespace, right? And here are all the things that are in the CSV module that are public, the ones that I can see. There's CSV reader, CSV writer, and you can see, interesting, its name is underscore CSV reader. That has to do with how it's implemented, I think. I think it's a C extension. CSV spam is not there. I don't get a name error, I get an attribute error. Okay, but very similar. I can do that if I want. Don't do that. I can do that if I want. Please don't do that. Right? Okay. So from CSV import reader as CSV reader, right? So here what I'm doing, again, you know what this does, but I want you to think about the names. This is all about names today, this afternoon at least, right? I want you to think about the names from CSV import reader as CSV reader. So I'm saying I want the name CSV reader to be in my namespace, right? And so I do that. And now I've got the name CSV reader added to my namespace. And I can check, is the attribute reader on this module that's already in my namespace in there? And it's the same? Yes, it's the same one, right? And I can see CSV is that module, and I can see CSV writer. Told you not to do it. It's still there. Okay, well, at least we could, okay, let's del CSV and import CSV as module. And look, okay, so I got rid of the CSV module. Right, so del CSV is a namespace operation, everyone says. Right, and then I import it now as CSV underscore module. So I'm saying don't import, go find the CSV module, import it as the name CSV underscore module. So now I've got those two. And CSV module reader is CSV reader. Good, those are the same ones. So now CSV reader should be, oh, it's still writer. Well, why is that? Because modules don't get re-imported every time you import, right? Once they're imported, Python remembers them, and it will remember them. And when you ask for it the next time, it's not going to go read and recompile that whole thing. That would be terribly inefficient, especially in large code where you've got this function imports that, and they all have lots of imports, right? So beware. All right. What happens if I type math? Anyone? Shout it out. Did I hear someone say name error? Name error. Okay, what if I type math plus 3? What am I going to get? Name error. All right. Okay, well, how about if I del math? What am I going to get? What's that? Name error. I tried to access something that's not there. What if I try print math? What's it going to get? Name error. All together now. What happens if I import math? What do I get? Why don't I get a name error? Right? I just think it's kind of interesting. Some of you will go, oh, yeah, why don't I? And some of you go, well, of course. Those of you who are going, why don't you? It's because when you say import math, it's treating the word math as, it's breaking the rules and saying it's not going to access the name. It's going to define the name for you, right? Import CSV as CSV reader. It's adding CSV reader to the namespace. Import math is adding the name math to namespace. At the same time, it's taking the identifier, turning it into the name of a module to go look for, and go finds it and loads it and makes the local name that it just added or is adding refer to that object that it did. So kind of like def, where it takes the name and does two things with it, here it's doing two things with it too. It takes the name math, goes and looks for a module that has those 4 characters, and it also puts it in the current namespace. Okay, did I see a question? Yeah. So why? So the question or the comment was print in 2.7 was a statement. It's a function now. They could have done the same thing with import. I don't think there was a compelling reason to. Like print as a function has a lot of advantages that print as a statement got in the way of. I don't think there are any of the advantages. The advantage with import, we don't have to work around them, I don't think, because there are other ways to do the same thing, which I'll show you. That's my, again, I'm just inferring the decision they made, but. Okay, so I've imported math, and now when I access math, yes, so math is a name here, and it's also the name there. And now if I del math, I won't get the name error because it will actually remove it from my current namespace, right? But it's interesting, before it can remove it, it has to go find it. That's kind of odd, right? So that's why a number of people scratch their head up here. Why does it need to go find the object if it's just a namespace operation? Well, it needs to find the object so it can decrement its reference count. Okay, so what if we don't know the name of the module? Well, we can use import lib, and it's got an import module method function. Well, I don't know, callable. Doesn't matter if it's a method or a function or a under call method on an instance. It's a callable. All right, so now if I say math.py, I should get an answer, right? Or will I get a name error? Right? So import lib.import module is just a function. It doesn't do the magic that the import statement does. It does not have the power to go change the current namespace. Nobody should have that power except Python stuff, right? Like the import statement. It's up there, it lives up there in the high, like you can't just write functions that arbitrarily change namespaces. That's supposed to be hard, because if you start doing that, you're gonna make a mess, right? So, and you notice, by the way, it returned a value, right? So this is a function that returns a value. So now, if I do that and save that value, now will MathPy work? No, because I didn't change the current namespace. I did change the current namespace. I added the name math_module. I did not change the namespace by adding the word math. And so there is no py, whereas there is a math module.py. All right, so now you can, so why do we need to have import lib import module? Because sometimes you don't know the name of this. Like here, I'm using an object. Up here, I'm not using an object. I'm using an identifier at compile time, right? So that's the big, again, you knew that already, but now you're seeing it through a lens that's slightly different, because I've been hammering this thing about names at you all afternoon. Right? So so if I can say, I can do that, and then, or read it from input, or pull it off a file, configuration file or whatever, and then I can just do this, import module name, right? Now, some of you have seen through my guys, and you're gonna start shaking your head every single time. Right, so if I do import module name, it's gonna go look for a module by the name of module name. There is no such module name. All right, so what I need to do is this maybe, right? Import math. No, that's not gonna work either. Import math you can do, right? So again, this is all these errors are to show you this is exactly what import's doing. And it's not even that interesting, but I think again, I'm exercising your what's exactly going on with Python and names and namespaces. Here's here's a exercise for you, and we'll stop for the break now. The break is supposed to be 20 minutes. If we only have one, that's my vote. So I think it's 20 minutes. So we will start again at 3:15, and or maybe even a little bit beyond that. Let's say 20 minutes. And do people want 50? Who wants 15 minutes? Raise your hand. Who wants 20 minutes? Raise your hand. Okay, we'll go 20 minutes. So we'll start in about 23 minutes and do the import statement now or at the end of the break. Okay. So the break's not over yet. We still have a few minutes, but note two things. One is the SurveyMonkey link, which is, I believe, specific to this tutorial. surveymonkey.com/r/PyCon228. It's very helpful. The reason this tutorial is as good as it is instead of not quite as good is because I've gotten feedback in the past. So please keep giving me feedback and others. And then the second piece is a challenge there, the next one there. See if you can figure out what error that will give you without actually running it. So I think we'll start in about 2 minutes. If you haven't yet, do the 3.3 exercises. Okay, let's get going again. So first comment, SurveyMonkey survey, in case you didn't hear it. Second is one of the questions that came up during the break, well, one of the comments came up during the break is the code disassembly that I showed, where I said later, go look at this difference between these two code disassembly lines. It looks like it's failing in Python 3.6 under IPython for some reason. So I'm not sure what's going on there. And then someone asked me a question about del. What would happen if we did that? So without having run it, anyone rise to the challenge and figure out how is it going to fail? Yeah. Right. Yep. That's how it fails. And the hint to that, or the clue maybe, was back when we did del len. Oh no, what was it? It's when we did. Wasn't it del math? And it gave a name error, even though it didn't. No, that wasn't the hint. But that's similar, right? So think about del math when it hasn't been imported. That fails with a name error, even though it's a namespace operation. And del len fails with a name error, even though there is actually a name further out. And then this is kind of similar as Python. And it'd be interesting to disassemble that, and I think you'd see what's going on there, that it's going to have a local variable len, and then when it tries to run, when you run it and it tries to do it, it can't find the local variable len. Yep. Is it true? Yes. If I scroll far enough back, you would see namespace operations always happen in the local namespace. Would that be breaking the rule of a namespace operation happening in the local namespace? It would be, because global is not in the local namespace. Now, if you use the global name, no, you can't change the variable. We don't have variables in this tutorial. Question is, can you change the name or the object, right? And really, it's about the name. If you access the name X and you've said global X, then you're not accessing a local name, you're accessing the global name. So then the question is, can you do a del of X if it's a global X? I don't know. I doubt it. And same error, or is it slightly different error? Okay, interesting. And that's yeah, it was one of those little edges again. One of those like that. Again, I've run across lots of errors where we could have written a long paragraph to say, well, actually, here's exactly the kind of error you're getting and why. What's the value, right? People who are working on Python are tackling more important issues than that. Okay, so let's look at here. What did you do? You tried to do it. You did import CSV. You did import lib, and then you looked at reload. So there's a reload module. If you're using Jupyter Notebook, there's an auto reload magic, but reloading is occasionally important. Rarely, I would say very rarely, should be important in production code. But if you're just working with stuff, you'd like to be able to, as you're doing development, it's really helpful. In that case, auto reload's more helpful. So here we'll do a del CSV. Okay. Right. Yeah. So again, why? Well, it's because import lib.reload. Reload wants a string, not a name. No, it doesn't. Or does it? Let's see. Oh, apparently it doesn't want a string either. Okay. Once it's imported, then can we say that? No, that's not going to work either. Well, maybe we should read the error message. Oh, raise type error. Reload argument must be module. Okay. How many of you actually read error messages when they show up? And if you admit that you don't? One of the biggest, I think, newbie failures is like I mentor a lot of people we hire, and some of them are new, as in young and new, and just skim right past the error message. Just slow down, read the error message. It actually helps sometimes. And part of that is, I mean, if you've worked, I mean, some programming languages, you want to go find the error in the 7,000 line output. It's good luck. Python at least doesn't do that, or sometimes it does maybe, but I think the culture is raise an error if it's going to be an error. Anyway, I'm distracted. So this will work. Pass it a module. It will go find it, reload it from disk, and replace whatever was already in its module cache with something else, with the newer version. Okay. Augmented assignment statements. So let's bind two names and reassign one. So here I'm going to say string 1 equals string 2 equals ABC. Right? And we know that syntax of that, what that means is make both these names refer to that object. And now I'm going to say string 2 equals string 2 plus D. So ABC concatenated with D is going to give me a string ABCD, and string 2 is going to become, that name is going to now refer to that new ABCD object. And I can see that they're not the same object anymore, and they have two different contents. The names refer to two different objects. Right? Okay, let's try with list. Yeah, and if I do the same thing here, right? So very similar behavior. Now let's change, instead of string equals string plus, or list equals list plus, let's try string plus equal. So we'll reset those names, string 2 plus equal D, and I get the same answer. They're not the same object anymore. They have two different values, two different objects. They are two different objects, those two names refer to. And then we do it with list, and we get something different. Why are those different? Well, the answer is that the plus equal in foo plus equal 1 is not just syntactic sugar. Okay, so plus equal is one of these edge cases. It's very well documented, but if you're not looking for it, you're not aware of it, you might go, oh, what's going on? These actually have their own bytecodes and methods, right? The plus equals is its own operator. And, is this going to work in Python 3.6? Let's find out. Looks like maybe it is. Oh, good. So this is at least showing you what I want you to see, which is binary add, in place add. So if I change the equal and put a plus down there, and I'll plus equal, I've got two different byte codes. It's a different animal entirely. So how does it work? Well, if we do list2 equals that, there's list2. If I call iadd on it, the first thing to notice is it actually returns a value. And the other thing to notice is it changed the list. Right? So ABC was the old list. Now ABCD is the list. It gets returned by the dunder iadd method. Right? If I call this one, I cannot call that one. But didn't I call that one? What's going on here? There's an in-place add, name1 plus equals name2. There's no type information in here. What's going on? And the answer is, what happens is, in-place add as a byte code, it goes and looks for dunder iadd, and if it can't find it, it says, oh, str doesn't have a dunder iadd, which we just found out because we tried to call it directly. Then it calls add and does the reassignment for you. Okay, so that's some part of the functionality of the in-place add byte code. Blah, blah, blah. The method should attempt to do the operation in place, modifying self, and return the result, which could be, but it does not have to be self. So here's the exact precise definition of how it's supposed to work. If the specific method is not defined, the augmented assignment falls back to the normal methods, right? Whereas it does that part. All right. Let's see that with tuple. It's still Thursday, right? Right. Int object has no attribute iadd. Good. And it doesn't support item assignment, right? So we know that that iadd fails, and then we know that tuple does not support item assignment. They're tuples are immutable. You can't change them, right? And if we do that, well, same thing. It's immutable. Can't do that. And of course, it has not changed. It's still 7. But we can do this. All right. So there's tuple2. Oh, phew. Tuple object does not support item assignment. That's good. It only gave me that error. Do you think it hid the other error, or was there another error? Does the list 12,13 have a dunder iadd? Yeah, it does. Okay, well, let's look at tuple2 and see that it actually, by the time it got to figuring out it wasn't supposed to do the assignment, it had already called dunder iadd on the list, and it actually made the change. So this is another one of these famous warts in Python, is that you get this error, but it actually made the change, right? So could we fix this? I'm sure we could. And how much slower would Python be to handle that weird edge case? If you want to understand, let's try to understand why it's doing this. So if we sort of unpack it and say, there's the list, there's the tuple2. It's Thursday. So if we try to call the iadd, it works and does the add. And we can see that it actually is, it's the same list, right? And then we look at tuple2, so we can see that it already changed, and then this is the second half of what happens in that, and that's where we get the type error. So you can this is just sort of breaking into separate pieces what implicitly happens in that case. And if you want to do some more disassembly, you can look there, and of course start by looking to see if it's actually the same. It's actually doing the right thing, or is it just let you check. And then there's some more stuff here. Okay, questions? Function arguments. Can functions modify the arguments passed to them? Okay, so what happens when I pass an argument to a function is a local name is created in the body of the function in that scope while it's executing, and it refers to, it's bound to the object that was passed into the function, possibly by dereferencing another name somewhere, but that doesn't matter. The function doesn't know about that. All it knows is it gets an object reference and it can get to it with the name that was defined in the signature. Okay, so if we do that, so we're going to try to take the string that comes in and change it, right? I'm putting quotes around it because you can't change strings, and we know this is going to do the fallback to actually just creating a new one and rebinding the name. So let's say we got string 1 and we call function, and we see inside there at point A, I got the one that was sent in, and then I got 1, 2 after the change. And if I look at the string 1 before we called it, it hasn't changed. It's still the string 1. And if you compare that, and you may not be able to see it as I scroll back and forth, but if you compare how this function looks and how it's called, if I change it here to use, so I'm going to change this line, and I'm also going to pass in a literal. I'm not even going to pass it a name. Well, I'm not passing either. I'm passing an object. But in one case, I did the function call using a literal. In the other, I called the function using a name in my local namespace that get dereferenced. In both cases, it's an object reference that gets passed. Right. So I call it. I get the 1, 2. Right. And of course, when we're done, and I forgot to show you that. Then, oh, okay, yeah, that's why I forgot to do it, because I would have to type this, right? Like I was going to show you that the name hadn't changed. Well, it's because I didn't even pass a name, so it doesn't have to show you. I passed it a literal. And obviously the literal string 1 didn't get changed to 1, 2, because you can't change strings. They're immutable. Like Python never reaches inside and changes the contents of that string. It just creates new ones. Okay, so that explains what I just described to you. If we do it with a list, right, we call function list1, and now what's list1 going to have? The name list1 outside the function is going to refer to which? The old value of the list or the new value of the list? The old version of the list or the new version of the list? What's that? The new, right? And like this should be really obvious. At this point, you should be going, yeah, why are you telling me this? For some of you, this will be more clear now why this works the way it does, because we've talked about names and objects and even the dunder IAD, right? Because some people ask, well, can you change something you pass to a function in Python? Well, the answer is it depends. And it depends on what you're passing and what operations you can call on that function. The only thing that's really confusing maybe here is that I'm using the same syntax, plus equal, a very similar syntax, and I'm using the augmented assignment, sorry. Okay. What's going on? Did it go? Any questions before we move on? Classes. So a class statement starts the blocks of code, creates a new namespace, very much like a function. All namespace changes in the block, simple assignment, function definitions, are made in that new namespace. So kind of like a function. When you use a name in a function, it's assumed, like if you assign a name, any namespace operation in a function, it assumes it happens in that function. Well, here we're actually doing more. These pieces are going to become attributes of the class and instances of it. And then the class name is added to the namespace. So here's a simple little class. It's got a dunder version attribute, a dunder init, dunder an add method. Self is the first argument, named self by convention. You can name it whatever you want. All right. Okay. So similar to functions, the name number right here went two places. It went into the namespace because the class statement is a namespace operation, and it went into the object that got created. Sort of the same way that a function knows its own name, at least the name it was created with. Okay, and I look at the if I can see where it gets yes, numbers class name is actually type. So the name of the class, but the name of the class is, I think that's a typo. I think this is supposed to be number.name. Makes more sense, unless I've forgotten what I was trying to show you. Okay, and I can see it, the number is the version. Instances of classes are called by calling the class, right? So when you instantiate a class, dunder init is called automatically. It is passed, for those of you coming from some other languages where it's slightly different, it is passed the instance, an instance of the class already created by a call to the dunder new method, right? So some people call these constructors. In Python, these aren't constructors, really. They're you're instantiating a class, but it's not the same. You don't do the allocation of the actual, you don't create the object. Python does that already. You just initialize it once it's been created. Okay, so let's go ahead and create one. This might be feeling slow to a few of you right now, because again, I'm slowing down to make it really clear, and then we're going to do some fun stuff. I hope it's fun. All right, so we instantiate a class. There's an instance. So we access an attribute such as add on a class instance, number 1. It returns a method object if add exists as a method in number or its superclasses. A method object binds the class instance as the first argument to the method. I know you're never supposed to read your slides. I want to make sure that that's the precise definition. Let's see if we can understand that by trying some things, or understand it in a little bit deeper and see what's going on. All right, so there's the bound method number.add of the number object. Which object? The class number that's living, that has a name in the current namespace, right? So then I can call it, right? So I call it like that, and I get 3. And why did I get 3? Well, because when it was instantiated, it saved whatever I passed in as self.amount, and later it used self.amount and added whatever I passed in. So it was 2, and I get back a 3. Sorry, it was 1. I got back, added 2, and I got back a 3. Oh, the class statement is just a way to call a function, take the result, and put it into a namespace. Very good talk from PyCon 2010. I encourage you to go watch it. Here's what Cliff is talking about. Type you've seen as a function. You pass it an object, and it tells you what type the object is an instance of. You can also call it with 3 arguments, name, bases, and dict. And when you do that, you're basically manually doing what the class statement does for you automatically. So let's define a function, not a method, at the top level, not in the class. We'll call it init, not dunder init, and we'll have the same argument self. We'll have the same argument names, parameters, and we'll have the same body of the function. All right, so we'll do that. And similarly, let's add as a function at the in this namespace, not as a method in the number class. Now, if I do this, and all the comment you're missing at the bottom right there is dict of class contents. So this does the same thing. This is identical to what the class statement does. Okay, and here you can see the numbers, the name, the number, that string gets put in 2 places. Here's the assignment into the current namespace, and here's where it gets passed off to the type function that actually stuffs it inside the object that the type function returns. Here's the list of superclasses, which in Python, oh, interesting. This may be a typo. I don't like in Python 3. You don't have to subclass objects to get new style classes because there only are new style classes. Then, if that's true, then it may be that this object is not necessary. That may be a typo. And then I pass it a dictionary, which has dunder version, dunder init, and add. And for each of those, it has the value, and the values here are those 2 functions. Okay, so let's do that. So now let's instantiate. And what's its type? Its type is main number. Why is it main number? Well, because here's the name and here's the name. So it's so interesting. So the name number here got stuffed into. It knows its name is main number. Okay, number 2's class is main number. Yeah. Okay, there's the dict where it stores the attributes, and there's the amount, and I can call number add 2.3. Okay, so that's pretty straightforward. Try this and see what you get. Okay, hang on. I'm going to apologize. In my edits last week, I left out part of this. So you got the first part. It's not going to teach you anything, but it will later. So don't throw away what you've typed in if you have. And let's go see some other stuff first. Actually, give me just a second here. Yeah, no, it shows up later. Okay, so sorry about that. So here's the class number, same as it was before. I just want to, except I added a print down here. Otherwise, I'm just repeating it so it's fresh in your mind. Let's poke around with this class a little bit. In this class, there's the numbers version, numbers under doc. Okay, so here I put a doc string, which gets stuck in there as its underscore doc attribute. If I'd called type directly, I would have had to put it in as a dunder, as part of the dictionary that gets passed in. If I do help number, it gives me all sorts of stuff that I didn't type in, right? So it actually goes and collects this information and tries to make it pretty for you. What are the, like the dunder init, dunder add, etc. All right, so number dunder init. So that says function main number dunder init. Doesn't say method. Number add, function main number add. Okay, doesn't say method because I'm accessing it on the class. If I look at what's in the number class, bunch of stuff, including a dunder init and an add. If I just look at the public stuff of it, you can see the only thing that's not starting with an underscore is add. So let's create an instance like we did before. I can access the attribute number amount, which is got put in there as self.amount in the dunder init method. Right. Okay, so here, notice that number.dunder init is different than number.dunder init. Here I got function main number init. Here I got, bound method number init of main number object at blah, 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 4e22140, 4e22140. So that's, for some of you, you're already going, oh, that's how it works. The rest of you, you'll be there soon. So add similarly is a bound method. If I look at what are the attributes there, well, I've got add is one of the public pieces that you can see under the sub-public attributes, and so is amount. So remember earlier when I said dir, if you pass it no arguments, shows you current namespace. If you pass it an argument, it shows you the attributes of that object. Well, add is not an attribute of number 2, but dir will tell you it is because it's an instance of a class and it gets to go up the tree looking for things. Okay, just like like you can access add as an attribute of number 2. There's proof. Therefore, dir shows it to you as an attribute that's accessible from number 2. Okay, and what is different between these two? Well, only amount. So that shows you amount is the stuff that'll basically give you the class instance or the fields. Sorry, the instance variables or fields of the class. And you can see this is where it actually stores the value in its dunder dict. Number dunder dict, as in the class, actually has its own mapping proxy. Okay, that's interesting. Question is add in there? And the answer is yes. Okay, number2.add. It's a bound method. So if I call number2 add 3, it works, and I get the call. It tells me it got called. So let's try something slightly different here. Everybody with me? Am I going too fast? Too slow? Not too far either way. All right, number add. Let's redefine the function same way as I did before. Remember, I defined it as a method early on, and I said, well, let's just before we called type manually, the type function. And I said, well, let's just define a function add. So let's define the function add again, just so you can see it. So if I, a number add, okay, so remember add is a function, like add is an attribute of the number class. It's that add method that was defined earlier, not this one. And when I try to call it directly, it says add missing one required positional argument value. Well, let's try calling it with 2 arguments. Actually, this is, when I say this is the earlier definition, both when I did it outside and inside. So this is the same as the method. Remember, it's the method add, takes self, add value as parameters, and it returns self dot amount plus value. So I passed it the right number of parameters, 2, 1, 2, and the reason it failed is because the first parameter, self, got the integer 2, the second parameter value got the 3, and it tried to do self dot amount, and it says the int object 2 has no attribute amount, right? Well, what if I pass it an object that does have a dot amount attribute, like this? Because number 2 has that dot amount attribute. Then it works. Okay? Of course, this is the right way to do it. Here's what the init looks like. Right? If we look at number init, yeah, we can do help. Yeah, okay, let's try something else here. Let's monkey patch. Let's create a new function, set double amount, which takes, just for fun, I'm going to change the word number, self to the word number, just because I told you before it's just convention, so let's break the convention. And it's going to do the same thing as the dunder init did earlier, except it's going to double the first, the second. The first argument is number. The second one is going to double that and then save it as an attribute of the first argument. Okay. And then let's monkey patch, right? So we're basically going to, on the fly, take that method out and put a different method in. It's not, usually when people think monkey patching, they're thinking testing, and one of the nice things, it always puts it back when you're done. I'm only doing the first part here. All right, and okay, number dot dunder emit. So similarly, it says it's a function, and it can get at it. The function itself thinks it's called set double amount, because that's how I defined it up here. If I do help on it, it's going to look okay. All right, so number 4 equals number 2. Is it true? Does number 4's amount actually equal to 4? Yes. All right, so that seemed to work. And can I do this? Yes, I got 9. Okay, so I just monkey patched numbers dot dunder init to be my own init that's slightly different. Right, so I didn't do that by changing the code that defined the class. After the class object was created, I went in and said, use this thing instead. Bound method, that looks good. Yeah, and it's true both for number 4 and for number 2. Right? Number 4 was instantiated from the number object, the class, after I monkey patched. Number 2 was instantiated before I monkey patched. But when I access number 2's dunder init, I get the same bound method. So the monkey patching has affected all the instances of the number class that were created before the monkey patch, which makes sense because it's not storing that code in every single instance. It's only storing it in the class. When you access it in the instance, it goes and looks at the class to find it and then returns this bound method thing. Okay. Let's add a new function to our namespace called multiply by, which has the same pattern, number dot amount star value, as the add. And then let's add it there, number 4 dot mul. So now if I look at number 4 dot mul, I can see it, but I get an error. But that works. So what's the error that I made? How did I monkey patch this? I monkey patched the instance instead of the class. Right? So what I did up here is I said number.init. The class's init method is going to be that object instead of what it used to be. Down here, I said number 4. The instance's attribute called mul is going to be that function, right? And that's why it's saying it's not right. Okay, well, hang on there. If you don't get it yet, keep looking. All right, so number 10 equals number 5. That works. Number 10.mul. Okay, so what's this going to do? It gives an error. I'm not going to show you the rest of it. What attribute is it not finding? Well, okay, fine, I'll show you. Number object has no attribute. Right? So you notice I'm accessing the instance number 10 of the number class, and I'm trying to access its mul attribute. And it's telling me, sorry, I can't find mul. And where does it tell it you can't find it? It says it can't find it. It's not telling me it can't find it on number 10. It's saying it can't find it on the class of which number 10 is an instance, because it's doing the rules, right? It's not a problem if it can't find an attribute on the instance, because it goes and looks in the class, but it gets the class and it can't find it. Why? Because we didn't monkey patch the class. All right, so we can see here, there's the add and there's the amount. We look up here, we see it only has, there's the add, and we look at that one, it's got the add, the amount, and the mul, right? So number 10 has amount as its instance variable. The self.amount we created in dunder init. It's got add, but it doesn't have mul like number 4 does, because, all right, so because we put it in the wrong place. So now let's do number 4.mul equals multiply by. So now I have correctly monkey patched the number class. And now I can say number 10.mul and I get 50. And now I can say number 4.mul and I still get a type error. Why? No one's got their pen out drawing on the paper. But you probably are in your heads, right? So if I look at the what's on number 4, well, yeah, it's got what I expected it to, but where does it have it, right? So it has, so when I do a dir, it says, yeah, I can find these attributes for you, but instead of finding them add in the class, amount in the instance, and mul in the class, it's finding add in the class, amount in the instance, and mul in the instance, right? So I had the number class, I monkey patched the instance. Oops, that was a mistake. So I monkey patched the class and then created a new instance, and that instance finds the method correctly, but this one still has the incorrectly monkey patched instance variable right here, right? So to fix that, I remove that. I look to see that it's actually gone. I check to see that it still looks like the public add amount mul didn't change, but the mul one, instead of getting from the instance as a function, is now getting from the class as a method. It's a function in the it's a function in the class that becomes a method when it's accessed. Okay. And if I look at number 4.mul, you can see it's now bound method of the number object, as opposed to, did I actually do a number? Yeah, number 4. I should add number 4.mul there. Hang on a second. Thanks for your patience while I make it better for the next class. Okay. Okay. So, is it making sense here? When I access an attribute of an instance, it goes and finds it in the class. It does something and returns a bound method, as opposed to the function that is what it is when it's up in the class. And of course, it now works. Okay. We're almost done this long section. So number 4, Number.add is a function. Number4.add is a bound method. You can actually use bound methods directly if you want, like this. Use them directly. You can use them always directly, but you can rename them if you want. They're still useful. Like number4.add returns a bound method object. You can save that bound method object, as in give yourself a new name for it and use that name directly. And it's a function, right? So if you want a function called add to 4, well, there you go, just by accessing it there. And I think I have an example later on in one of the sections that shows another example of that. Here's another one. All right, so if I take the dunder_mul method of the integer 2, an instance of the integer class, it is a method wrapper, which is a little bit different than a bound method, but does roughly the same, entirely the same thing, I think. And now I can just use it like it's a name, so it's a callable, and I can call it like a function, which will double stuff, right? So if I double 3, I get 6. I double 4, I get 8. Last thing I think I'm going to show you, was there a question? Last thing I'm going to show you here is just to see how these work. So it's got the add amount and mul. So what does the bound method have as attributes? Call class, blah, 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 blah. Okay, and what does number4's? Only, what are the public ones? Not much. Well, what's the difference between the class's add function and the instance's add method? Ah, okay, there we go. So what does, when the bound method, the function is up in the class, I get back the bound method, it's got a lot of the same attributes, but it also has a dunder func and a dunder self. Let's see what those are. Dunder self, that looks familiar, doesn't it? That's the same address as number4. So number4's add bound method self attribute is a reference to the object. All right, and there's proof. And how about the func? What does the func have? Well, the func has a reference to, and here's proof, to the function, right? And they're all the same references, right? If you look at number4's add bound methods dunder func attribute, and number10's bound method add methods dunder func attribute, they both refer to the same object as numbers add function. I'm calling it add function just to distinguish it as the method defined up at the class level, right? So when I call number4.add, it's basically doing this line. So it's just remembering. All it's doing is remembering, like when you get the bound method, it's just saying, okay, yeah, here's the bound method is just a partial. It's a function partial that, or a partial function that knows about the object. Okay? So when you access the method in Python on an instance, what you get back is something that already knows about the instance, the self, and passes it off to the function when it gets called. That's how it works. And that's why those other ones like double and the other one worked as well. Okay. Here's a little exercise for you to see a more useful example for bound methods, of bound methods. I'll give you a couple minutes to do that. Okay, let's just look at this example quickly. All I'm doing here is importing keyword. Sorry, that should be a different cell type there. But basically, if you look at keyword key list, it's just a list of all the keywords. And list has a method called under contains, which just returns whether or not it's in there. So here's an example of another bound method. You want to create an is keyword function. Here's another way to do it. Yeah, these are kind of toy examples. There are a few cases. I have occasionally used this when it was not just a toy example. It just made sense. It was a lot easier to do it this way and even clearer. Okay. So we're on the home stretch. 20 minutes, right? We're done at 4:20, I think. So we're on the home stretch. I think we will get through 4 and 5 and not 6 and 7 as I predicted. I might get through first part 6. Anyway, meta classes. Anybody get kind of getting scared? These are meta classes. I used to get scared of meta classes. I still don't really know very much about them. I'm going to show you how they work and make you less scared. I'm by no stretch a meta class expert. I've written maybe 1 or 2 toy ones. But by thinking about names and namespaces, I go, oh, well, that's all they do. And so I'm going to get you past your fear, I hope, those of you who are afraid of meta classes. And then you'll at least know what they do and not go, oh, it's this weird, mysterious thing. It's like, oh, yeah, that's a cool thing that would be really hard to do right. So meta classes let us customize how classes get created. So usually you subclass type and override a bunch of stuff. The other thing you could do is, oh, wait, hang on. Did he say you subclass type? Isn't subclass a function? Well, we can call it as a function, but it's really a type. Again, at some level we don't care. It's a callable. Remember I said you can call type and pass it an instance, and it will show you the class of which the instance is an instance. And then I said you can call type and pass it 3 arguments, and it'll create a class for you. Well, it's a callable, and usually you would subclass that callable, which happens to be something you can subclass as opposed to a regular function. But I'm going to do it a simpler way, which is just change type entirely. Okay, by default classes, and I'll let you read this on your own because I already explained this. You can change it by using the meta class keyword. I'll show you how to do that. And here's an example. So this is a pretty simple function. It's basically the identity function, except it changes the name. It just changes the name, right? So I'm just going to call whatever I'm going to, oh, and then I'm going to make, so basically by saying in Python 3, meta class equal my meta class 1, it says use this thing, use this callable instead of the type callable, the built-in type callable. So what Python's going to do in this code here is it's going to get the name number, it's going to get the list of superclasses, which is empty here. So it's going to just call it with object. And then it's going to get these functions. It's going to go ahead and evaluate those functions and take all that stuff and pass it. Oh, that's interesting. Typo. It's going to take all those things and pass it off to not the type function, but to this instead. Okay? So if I call this, oh, did it work? Yes, it works. Okay, so all I've done here is just made explicit which was implicit, which is going to call the type callable. Okay, let's do something here. I'd like to be able to dump the contents of an instance, but I can't because it doesn't have such an attribute. So what I'm going to do here is add it. So my meta class 2, name, bases, dict, return type. So the only thing that changed are these 3 lines here, def dump print, so that 2-line function, and then whatever was passed in, that dict which was passed in, and that's not a great name, I'm overriding I'm not overriding, I'm shadowing a built-in type, so that's a bad name. But I'm going to add this function to the dictionary that gets passed off to type. So now when I use the class statement, but tell it to use my metaclass 2 as the metaclass, i.e. as the callable that it should use to construct the actual class object from the pieces that it collects when it reads the class statement. If I use that, then number1.dump works. Is that for a simple metaclass, right? All I'm doing here is what I did before is I created something that looks a lot like a method or a function. The only difference is I named itself the attribute, the argument passed in, just to because it looks more like a method to me then, and then it does whatever I want it to do. So that's how you create. That's the simplest way I can think of to create a metaclass, and it's not that hard. So do this exercise. I'll give you about. Not gonna give you. Let's do this one together, because we're almost out of time, and I would like to get through this last section. So let's see if we can understand what this does. So return spam is a function, sort of like my metaclass 1. It takes name, bases, and namespace. That's a better name than dict. It's got a docstring. It prints something out. It prints the arguments that were passed in, and then it doesn't return whatever. It doesn't call the type callable and pass the 3 arguments and return what that type callable built-in does. Instead, it just returns the string spam. Okay, so if I, hey, it works. It returns the string spam. So, and this will look familiar because it's the piece before I said do the exercise, and then I realized, oops, it's half there. It's because I didn't move the rest of it. Right. So if I say x equals return spam, x is clearly spam. So what will this do? Class y metaclass equals return spam. And the comments are just if using Python 2.7, they sit different syntax. So Python's going to collect a bunch of information from this. It's going to collect the name, the empty list of superclasses, classes from which it's going to inherit, and all the attributes in here, methods, class variables, etc., of which there are none, so that's why I stuck the pass in. It's going to take those 3 things, the name, the bases, and the namespace dictionary, hand it off to not the built-in type callable, but to this one instead. And then what it's supposed to do is whatever that thing returns is going to be the class object that gets inserted into the current namespace with the name y. Right? And it called it, passed off, oh, look what it passed it. So it passed it y, which is the name of the class. It passed it an empty tuple of superclasses, and it passed these attributes, which I didn't tell you about, but those are some of the ones that it collects. And now y is going to have, what's y? It's just spam. Right? So this just, my point here is, obviously this is a stupid metaclass. I would tell my second son, don't use the word stupid. You don't want to, but it is. It's just there to show you that that's all it's doing. Like, that's the rule of what metaclass does. It just overrides the regular, take this stuff and make a class object and assign it. It just overrides it with whatever you want to. And you can override like this way you want. It's a kind of a complicated way to make a string. But, okay. So, well, if we can do metaclasses, we can do decorators in 10 minutes, can't we? Yes, because I'm not going to show you much about them. I'm just going to show you the mechanics so you're not scared of them. Yes. 440. Marvelous. Is that true? Well, whoever wants to leave at 420, you're free to go, or leave now if you want. But thank you very much. That then I won't. I'm happier because I thought I was feeling a little tight. Okay. So any questions about class, metaclasses? You can all say you've written a metaclass now if you want. Just go type that stuff in. You're done. No, to do it, I don't mean to make fun of it. Metaclasses are very powerful. They're complicated, hard to get right. is my impression from not having written any other than these toy ones. I've used lots. They're wonderful. It's one of the nice things about Python is you can do all these things pretty easily. And Lefkowitz's talk does a great job of showing you how easy it is to do these things in Python. It's not that you can't do them in other languages, but many other languages make it very hard to do what's easy to do in Python, things like metaclasses. Okay, so here's a function add that, that's exciting, adds two numbers. Here's a function that returns another function, right? So if I call this function, we've seen this a few times, but now we're actually going to use it. We're going to call it to do something interesting, like adding two numbers. That is so interesting, as opposed to just printing the length of something. So what's going on here? It's going to create a function. Okay, it's hard. Maybe it's hard to think about this without an instance. So let's use this code to look at it. So if I call create adder with the number 2, first is going to get bound to the integer object 2. It's then going to call this, it's going to create a new function called adder, which takes an argument second. It's not going to, we haven't called that yet. We haven't called adder, so we don't know what second is. It's then going to return what? So that new function is going to call add, which is defined up above as adding its two arguments together. And whatever that function returns, we're going to return it. And then this create adder returns this function inside that's in the local scope, gets returned out. Now notice this add here. The second only gets bound when the adder function is called. The first argument gets bound when create adder is called. Okay, so let's define that and let's call it. So now add to 2 is this adder function. It takes a single argument, like the 3 I'm about to call it with. It calls the add function from up there, passing it first, which is the 2, and second, which is going to be the 3. And it works. So if I want to create adder add to 2, if I want to create a function that adds 2 to whatever I pass it, I can call the create adder function, passing it the number 2, and it will give me back a function that does what I told it to. Create me a function that adds something to whatever you pass it, where the something is the variable here, the 2. I can vary this 2 to be anything else. Okay? Let's look at a more complicated, well, not really more complicated, but more interesting maybe, a function that accepts a function as an argument. Ooh, okay, so this one, we've got a function that returns a function, but it takes integers the way we used it. Here I've got a function that takes a function as an argument. Okay, so if I call trace function and pass it a function, it returns a new function. It returns a new function, which is defined this way. What does it do? Well, it calls the original function, passing whatever args it is passed, and before it's called, it prints out what it was called with. After it's called, it prints out what was returned, and then it returns a result. So all I've done is just put some stuff in to say before and after. I'm going to instrument or trace it and say, tell you what's happening, right? So let's define that. So if I take the add function, remember the add function was the simple one up there? If I take that add function and I call it to trace, I call trace function, passing the add function, I get back a new function that does some prints, then calls add with whatever arguments it's called with, and then returns the same value. So if I now, let's try it out. Let's try traced add 2, 3. There we go. Look at that. You can just barely see both, I think, right? There's the print called and the print returning, called, returning, and it returns 5. All right? So now I've got this traced add, but I could do this instead. I could do add equals trace function add and just overwrite, like the original function here, this name add refers to the original function. I'm going to make add in this namespace refer to the new function that gets returned, right? Now, is that a problem? When I call trace function, that original function I passed in, is it gone? Does it get garbage collected by Python? No, it doesn't. Why does it not get garbage collected by Python? Because its name is still used. There's still a reference to it. So that function is still around. I just can't get at it directly. Right? So now if I call add23, there we go. It tells me what it was called with, and it returns 5. Okay? So if that was clear, and I'm not sure it was for everyone, this is like for some people it's like, yeah, this is easy, but others it's hard to think at this level. I know for me it's, this does not come naturally to me to think about these things at these meta levels. So add equals trace function add. This right here does all of that in one fell swoop, one step. So if I put an @ sign and a name here, and then a function definition, what Python will do is it will create the object that the object that the definition creates, the function object. We've looked at that, right? We've looked, it's got code, under code, and it's got arg count and all those things, and some code in there, obviously byte codes, whatever. It's going to take that thing, it's going to pass that function off to whatever this name refers to, which is a function, and then whatever that function returns is what's going to be put into the current namespace with the name add. That's all a decorator does. That's it. So decorators are not super magic, they're just super powerful. Okay? So let's try it out. Ta-da, ta-da. See? It works. And if I look at add, whoa. Function main, trace function, locals, new func. Function main, locals, new func, right? It's going in there and it gives you, in Python 3, it gives you a very helpful, you can go find where that thing came from, right? So in dunder main, there was a trace function that I defined, and it's got locals in it. One of those was new func, and that's the name of this thing, all right? Now adds, and there it is in qual name, and the doc is the new function, not very helpful. So I can add one line right here, functools.wraps, and the only difference will be, so I just changed the trace function by adding this one line, functools.wraps, and what functools.wraps does, that's better. Add. So now it looks like the right one. So all functools.wraps does is it itself is a decorator that takes information it has from down in here and from in here, the add function, and wires it back together the way you would think it should be, so that error messages look right. Right? And you know how to do that now because you've seen the dunder code and dunder code arg count and all that kind of stuff. Dunder qual name. You see how Python's wired these things together. Okay. Oh, one more level. To write a decorator that takes parameters. How do you write a decorator that takes parameters? Well, a good way to think about that is to actually start here. So suppose I have a function concat, right there, and I want to, if I decorate it, what am I decorating it with? Am I decorating it with that? No, what did I say? Python looks at what's after the @ evaluates it, right? So earlier I said it takes the name. So let's go back and look at this. So this is actually an expression that Python evaluates. And in that case, it's a pretty simple evaluation. It looks up the name. In this case, it's a slightly more complicated evaluation. It looks up the name and calls it, passing uppercase equal false. So if I want a decorator, hang on a second. If I want a decorator that can take arguments, it needs to be a function that returns a decorator. Yeah. Do I need this argument? I Here? No, I don't. It's a default argument, so I could have left it out. But I have to have the open close paren. The open close, the round brackets, the parentheses. I have to call that. So dereference that to get that function, call it, and whatever it returns is the function to which I'm going to pass the concat function, right? So now let's see how it works. What does it do? Well, okay, so it takes uppercase equal false by default, and it defines trace function. Well, that looks familiar, doesn't it? All of that is almost the same as all of this. The only difference is I added these two lines. So all I did is push this function one level deeper, right? And so now the better trace function, when you call it with an argument, returns a function. What function returns this function? Right? So again, what gets returned from better trace function? Right here is the return from better trace function. Down here, return trace function. What is trace function? It's this function that I define in this better trace function. Right? And so the reason I'm adding stuff here is because I want to change the behavior. I want a more general trace function that can be uppercase or not. Right? So then this is the function that will actually be the decorator that it gets called. But it has access to, right here, it has access to an argument that was called here. So it's binding that. It's another closure. All right, so let's try it out. Actually, we better define it before we try it out. There we go. So there you see the difference. So the result, we uppercase it. If here we don't uppercase it, so we get spam eggs right here in the print. Oh, actually not in the print, in the return. The actual return value. We're actually taking the return value and calling the upper attribute method on it. Okay. Is anybody's brain hurt looking at that? It's like this level, this level, this level. But you get it. You get it now, I hope. My hope is that you go, oh, okay, yeah, I get it. But that's why a decorator, okay, a decorator is kind of hard. It takes a decorator. Well, it's really not that hard, except it's one more level of meta thinking, kind of, or indirection there. Okay. Yeah, so decorator is a function. Okay, so this looks very familiar. Return spam. So there's a function that no matter what you call it with, will tell it how it was called and then return the word spam. And there's a function that does nothing. And that function, okay, so let's, if I call return spam, pass it the function x, and then reassign it to x, i.e. rebind the name x to the new object returned by return spam, then x is going to be, okay, x is going to be spam, right? That's pretty obvious. Well, then what's this going to do? All right, again, and this toy example that forces you to think about exactly what decorators do. Take this function definition, pass it as an object, as the only argument to whatever this refers to, which is the function return spam, and whatever it returns is what I want to put in the current namespace with the name x. And we know what return spam always returns, regardless of what function we decorate with it. And that is, it always returns the string spam, so it's going to return spam. And again, yeah, well, I think I've said it 3 times now. Stupid example, but helps you say, oh yeah, that's all that decorators do. Decorators, I guess where I could argue with my son and say, it's okay for me to use this word stupid here because Python decorator, it's not gonna, like, it's just going to do exactly what you told it. And if you have a function that just is stupid as it just returns the string spam, it will say, okay, that's what you wanted, I'll do it. It's not going to check that it's actually returning a callable or anything else. It doesn't do any of that. It lets you worry about those details. Here's a similar kind of thing. You can actually apply decorators to a class. I'm going to skip that part because you can look at it and it won't reinforce anything. Like either you're to the point where like, oh, you'll get that immediately, or like, oh, this is hard to think about too. So do it later when you've recovered. Okay, so we've covered a whole bunch of stuff related to names. Assignment, unbinding, importing, defining functions, the bodies of functions, classes, globals. 4, here's ones we haven't. Oh, the try, this one we did cover actually. 4, name in and list comprehensions and generate expressions. There's a name that gets created there. With as name, there's another one. And set adder, we sort of, we kind of looked at it with the dunder set adder. So let's look at some of these special methods of classes. Attributes access and descriptors. So dunder get adder, dunder get attribute, set adder, del adder, dir get, set, delete. All bunch of stuff. I didn't put in del because del is not a namespace operation. You notice it's del adder. Del is something else. Okay, so let's look at a simple example of how changing how a class handles attribute access. This is one of the sort of behind the scenes features in Python that I've used a fair amount, like 3 or 4 times in the last several years, because it made code that could have been really boilerplate and just long and drawn out and error prone way better. You have to think a little bit harder about a lot less code. So this is a class that returns uppercase values on uppercase attribute access. Okay, so what's it going to do? Well, it's a class. Yeah. So there's no dunder init here. There's no methods. There's no public methods here. This class. All it has is dunder get adder, right? So if I try to access an attribute, it's going to call this. No, if I try to access an attribute on an instance of this class, and it finds it in the dunder dict, Python will return it, and this code will never get called. If, however, it can't find it, then it will say, well, is there a dunder get adder? Ah, there is. I'll call dunder get adder and let it handle it to see if there's something it can figure out what to do. So this is only called if we call it with an attribute that does not exist. So let me show you down here an example of that. So I'm going to create an attribute, access the attribute, and then I'm going to access an attribute that does not exist. There's the use case. Right? And so what it's going to do is all it gets is the name of the attribute as a string, right? Not as an identifier or a name. Like it's a string that it's the name is the name of the name. So I'm going to check if it's upper, then check to see if its lowercase version is in the dunder dict, which is where it looks for these attributes. If it is, then lowercase it and go grab it, and uppercase it. So lowercase the name to go grab the lowercase is not the most efficient code. To go find it in the dict, uppercase the value you find in that key value pair in the dict, and return that. And then this part's really important here. If it can't find it, you got to raise attribute error. If you get these wrong, you can get infinite loops pretty quick. Okay, so let's try that and see if it works. All right, there's my dict. It's empty. It's an instance of a class. I can just add attributes, sort of like simple namespace, right? So there I got it, dfoo, and there's the dunder dict. And now, voila. Right, so it both works. So this is not an attribute. The only attributes in self dunder dict is lowercase foo. Uppercase foo, it does the right thing with, because I told it if they ask for the uppercase attribute, give it the uppercase value. Baz, it fails, or fails as it should with an attribute error. because I told it to raise that attribute here. Okay? Another example. I think I have another example here. Oh, no, we're going to talk about decorators. Sorry, not decorators. Properties. Properties are a nice feature in Python. How many people haven't seen properties before? Or not much? Have not? Okay, quite a few of you have not. So if you are trying to design something and you really want to get it right the first time, and you say, okay, we want to be able to change how this attribute behaves in the future, and maybe we should make people go through a method to get at it. Don't. Just let them access it. And if down the road you change your mind and you want to control it somehow, you can add a property. And it makes it easier, it makes it faster to code. You don't have to solve the problem before it shows up. And it makes it easier for users. They can just access attributes in their intuitive way without always calling a function to get back a value. So here's how properties work. Here's my property example class. Nothing terribly interesting there. I just have this underscore x that for each instance of this class will start with uninitialized as the string. And then I've got def x. So the method x, if you call it, it prints this line and then it returns the value of underscore x. But I put at property in front of it, so it's decorated. And what that does is it means you can actually access it as though it is an attribute x. You don't have to call it like a function. So this defines the function that will actually get called when they try to access the attribute x. And once you've defined that, then you can use x.setter. So this property decorator does something cool and actually returns something that not only does it change not only does it do the right thing for the the getter, but it has an attribute on it which lets you decorate the setter and the deleter. So that's just kind of a neat way they design that. So this is what will get called when you try to set an attribute, and here's what will get called when you try to delete the attribute. And that's all you have to do. And these can do whatever you want. Here I'm just printing and returning. You could, convert from polar coordinates to Cartesian coordinates or whatever you want. You could have side effects. You could have lots of things. So let's create that. P.x uninitialized. All right. So there we go. P.x. So I accessed attribute x. There is no attribute x anywhere in here, but this makes it look like there is and gives it some behavior to actually do the right thing, which is print something and return it. Right? If I try to set it, it worked. Right? Gives you back the bar. So it does everything you expect it to do, but it's doing it, inserting some functionality in between the attribute access and what actually happens behind the scene. Similar to the way decorators inserted some functionality between the call to the function before and after it. Sort of like the way meta classes inserted some functionality in between when Python collects the class stuff and when it calls the type function. Okay. Here's another example of getAdder. It's kind of interesting, kind of fun, I think. Here are all the Python releases, not all of them, but all the most recent of the major releases. All right, so this code would work if I ran it. So I could do this. Release fields. I pass it a line, one of these lines. I want to get out 346 or the date or something like that, right? And so I saw the name is self.data 0 up to 6. Property, the version is that offset. So these are the 3 offsets I care about, so I'm going to pull them out of that string, right? So if I say here's the release, and I pass it off to the release fields class and create an instance of that, now I can actually access release.name, and it will get the right stuff, get the right stuff, get the right stuff for each one of those, right? So now this code, unless I change something, it works, right? But, suppose I had, 50 fields. And this is a real case I ran into about 8 years ago where I had about 40 file formats, which each had about 50 fields. And I didn't want to write 50 of these things times 40. So I did this instead. and I've simplified it here to make it fit on one slide. Functionality is exactly the same, and it's not much shorter, but if you, again, imagine 50 fields, 40 file types or something like that, then, and in fact, the code wasn't even Python code that got it. It actually went and read the specification document on what those field names and offsets and values and whatever, and just read those and created these things directly, right? So how does it work? Well, when we try to access release.name, release.version, or release.date, I've defined getAttr here. So this is going to be the name, version, or date. And it looks, okay, is name, version, or date in there? If so, then use look up the actual slice to get the value back and return it. Otherwise, return attribute error. So again, you'll just have to imagine, that this would be helpful in a larger. Cool. What did I get wrong? Thank you. And I think it's because just in case you don't care why, but it's because this one's not, there was a new one, or somehow since when I first put this in, I had to offset things. Okay. Oh yeah, and then this one, I want to make sure. Good. So I want to make sure it actually behaves the right way if I type it wrong. 4 minutes. That one you can do on your own. It's kind of interesting. Let me just show you what I haven't shown you. So, there's an example of first-class objects, which is kind of fun, and some more examples of binding data with functions, which is sort of the general idea of what bound method is, for example. And then I have a whole section on iteration generators, which again, I didn't think I would get to, but I encourage you to look at it afterwards. And it sure shows some toy examples of generators and how they're easier to read and write in addition to being lazy. I want to remind you what section was that we were looking at where I put the survey. Does anybody not have the survey link? Then go find it, or I'll bring it up here in a minute. I hope that was helpful. We learned a lot about names and namespaces, and I hope you're a little bit tired. That means I worked you hard, and well, maybe you're tired for other reasons. But thanks for coming, and feel free to reach out to me if you have questions, or stay afterwards and chat a little bit. Thanks. Function str.upper. Interesting, it doesn't say method. We might think about that later. I can call that method, and it will create a new object, right? So a string literal is an object. I'm slowing down again here. It has an attribute called upper. If I ask Python to show me to get that object, and then show me the representation, that's when I get back function str.upper. String literal is an object. If I do the same thing and then call that object, that called object is going to return another object, which is in this case a string object that looks like a string literal. I'm not going to ask how many of you are getting tired of me saying it slow. It will get better. Hang in there. If I look at what all the attributes are of the string object, I get a lot of them. So dir, when you pass it an object, shows you most of or some of the attributes, the main attributes of the object. There's a slightly more complicated definition I'm not going to cover. All the ones that start with the double underscores we call dunder, in case you haven't heard that spoken out loud before. It's a dunder add, dunder class, double underscore. And then there are a bunch of, here are the ones that are sort of the more public facing ones, or at least public and the ones you would usually use, which are capitalized, casefold, a whole bunch of them. Okay, so lots and lots of attributes on this object. Every object has a single type. one way to get at the type of an object, and this is not the recommended way, but you can do this, and we're going to do a lot of this, is go look at the attributes to see how Python keeps track of these things. So what happens here? 3.14, literal is read, a float object is created. It has a dunder class attribute. I dereference it or go find the object that that name refers to, and I get back an object. And when Python tries to show me that object via a string, I get back the word float. And we'll come back to that, of course. All right, and there's a string literal. So this is what type it is, right? That's a float, that's an str, that's a list, that's a dict. Same thing. So let's look at the base classes of float. So Python is multiply inheritance, so it has bases, which is the plural of base, because there may be more than one base class. 99% of the time, it's a tuple with a single element. So float 3.14 is an instance of float. Float is a subclass of object. You can look at the method resolution order via an attribute, and you see that float subclass is object. Slightly more interesting one. So when we say 1 equal 1, it's going to create an object. That object is of class bool. Its base class is int, and its base class is object. And its base class, one more, is empty. So we can see that the Boolean that got created there is an instance of bool, subclass int, subclass object. Some objects are created at startup, and they already have names, right? So an example would be the name capital T true. It's got the class. Well, it's the same one we saw before, really. We didn't see the object. We didn't see the string representation of it, but it was there. This should all be straightforward. So you notice that the IDs of those two objects are true. That means they actually are the same object. That's what is means. So in Python, equal means, are these two objects equal? By whatever definition Python or the implementer of the type or class that those objects are an instance of defines equal to mean. Right? So is 3.0 the same as 3? Well, no, they're going to be different objects. Are they equal? Well, that's up to those classes to decide. And so that's what is means. So we saw float before. This is an example of some of the built-in names, right? Float, and there it is there, and there's where the name is, right? So the word, when I access float, when I type float in the interactive prompt, Python looks it up in a namespace, goes and finds the object. When I type 3.14, Python goes off and creates a float object, and then I access its dunder class object, it's going to give me back the same object. And that object, when you try to print it out, when Python tries to show it to you, it's the word float, float. Okay? Okay. Here's an interesting one. What type does a type have? Well, types are of type. So there's float, there's type. So float's type is type. The class of which float is an instance, even though it's a class, is the type. And it's got an MRO, so type is a subclass of object, and it just, you can't get to the end of that chain. It just keeps going. Some built-in functions. There's one, function len. What class is it of? Well, what's it? It's an instance of built-in function or method. Don't worry about what that is exactly, and you'll see that we'll see later that different built-in functions happen to have different, be instances of different classes. It was whatever was convenient for the implementer. Okay, so to review, everything in Python at runtime is an object. It has a value, a type, base classes, a unique ID, and attributes. That's it. That's what defines a Python object. Usually, we can create objects other ways, like we call things. This section here, I think I meant to put lower. I just added it in recently and missed that. But we'll do this now. So let's do something first before I talk about that, how you usually create them. So let's import the sys module. GetRefCount is a function in the sys module that tells you how many references are there. Give me the reference count for a particular name or an object. It's the object. Okay, it's a question of how many names does that object have. And even the way I said that, how many names does the object have? I'll show you later. That may not be the right way to talk about it. There are multiple names. Well, let's just play with it and see. Okay, so there are 3 names out there in this Python interpreter right now that's running that refer to the object that got created when I did that right there. It's interesting. Why wouldn't there just be one? True, I can understand. There's lots of them. Any guesses on how many nuns are there running right now in the running namespace? Lots, that's right. 25,000, if that's what you said. I didn't hear it clearly. Object is going to be more than none. Actually, it's less, kind of interesting. Okay, so usually we create, often we create objects by calling other things, right? So len is this built-in function. I can ask if it's callable. I'll slow down again. What happens here is len is dereferenced to an object, which is the function, built-in function or method. Callable is dereferenced to another built-in function. A reference to that object that len refers to is passed off to the object that callable refers to, and that function executes and returns a new object, which is, in this case, true. So it's probably not a new object, it's probably the same one, but we can figure that out later if we want to. Okay, so then we actually call it, right? So every one of these is creating a new object, at least to simplify a little bit. Right? That's actually what len will call if it's there. Int's callable. Yep. Dict is callable. Most of the built-in types you can call them with nothing, and they will give you something, sort of the base case back. True is not callable. But bool is. 3.14 has lots of attributes. Those probably look familiar if you remember all of the 40-odd attributes that str had, but there are a few different. And there aren't very many functions, public functions, that aren't dunder functions. And there are a few other ones that have other interesting. I wonder what's going on there. I bet you didn't know that int had all those functions you could access, or attributes. I don't know if those are functions or attributes or something else. They are attributes. Sorry. Of course they're attributes. I don't know if they're functions or non-callables. Okay, so let's keep going. Oh, there's a method wrapper of float object. That's interesting. And it's callable. So let's call it. It expects one argument, got 0. Okay, let's try calling it with, okay. So we can see that's probably how addition is implemented on the float object. That one's not going to work, only because Python uses dot for more than one thing. But I can put parentheses around it and make it work. Oh, that's interesting. So you can't add floats to ints that way. Okay, so I'm going to take a break now. I've got lots of little short exercise sections. When you're doing the exercise, go ahead and type these in, see what you think they do. I'll review them afterwards. Partly it's just for you to think again about the same stuff. Partly it's just to give you a break from me talking. So I'll give you about 2 minutes to do that. I think most of you are done or getting close. So if I get the size of the string A, it's string, by the way, it's not a character. There is no character type in Python. There's only sequences of bytes or sequences of characters. In sequences of characters are called strings. So you would think the letter A, I mean, if we were writing this in C++, how much memory would the string A take? Maybe 2 bytes? This one's taken 50, right? And if I go up to 4 characters, it takes 53. So it looks like there's the base case, an empty string is probably 49. So there's a lot of memory being consumed, keeping track of what type this object is, what it's a subclass of, all sorts of stuff. Get size of 1, all the way up to 2 to the 30th minus 1 is 28. In Python 3, ints and long ints just magically seamless between them in at least most cases, or maybe all cases, I'm not sure. So you can see that when you start to get large enough numbers, it's going to take more than the 64 bits, and so it adds some more. Okay, so this is just proof that those objects are a lot bigger than they have to be if you were compiling this language. Question? They're all 24. Okay. Implementation detail. I don't know why that would be. I don't know enough about. Are you running 2? Python 2 something? You're running Python 3 as well. What's that? 3.6. Okay. Yep. But again, these are implementation specific, right? It gets compiled to a different architecture. I mean, obviously, if it's 32-bit machine versus 64, you might see a difference. But it depends on lots of things. Okay. So names. Let me talk about names more. I'm still talking about names. So understanding names, you really have to understand how they work. Almost every object is known by one or more names in one or more namespaces. So in the same namespace, you can have 2 names that refer to the same object, or you can have in 2 different namespaces the same name or different names that refer to the same object. Namespaces are like dictionaries, key value pairs, right? Except more specifically, it's name and a reference to the object. That's the key value pair. Names are bound to objects, or they are references to objects. Bound is the term that's used in the Python language spec often. Another way to think about names is it's like a post-it that you put on an object, right? So it's a label, right? Like I've got this laptop, then I put a post-it, I write post-it, or I write laptop, stick time to avoid the use of the word variable, and reserve that for when I'm talking about something that varies in the mathematical sense. So just to show you what sorry about that, what I mean by the compiler reserves memory. Like here, if you take this code and compile it down to machine code, you'll see that these 4 lines here are different. We've got a move-L, and imul versus a move-ss, mul-ss, right? And one is because I declared an int, and one is because I declared a float. So the compiler saw the declaration at compile time and said, oh, A is always going to contain a float. I will reserve a box in memory, a location in memory, and the float's going to be there. It might be on the stack, might be on the heap, who knows. Might be static. But basically, when someone does something to that memory location, if they do a multiplication, I have to remember that it's a float because I'm going to issue floating point instructions, the ones with the SS, instead of long integer instructions. So that's what I mean about the types and what the compiler traditionally does. So here's a rough overview of how we're going to do this. I'm going to talk about objects. That's going to be the slow part. And then basically I'm going to talk about names work the whole time. That's going to be the theme that runs throughout the tutorial, is how do we change namespaces, create names, remove names in Python. And then there's lots of stuff following that trail on either side that we're going to pick up and look at that's interesting in other ways too. Lots of examples. Don't expect to catch all of them. I'm going to use introspection and do things that I don't want you to do in code, especially not production code. I probably won't get to the last 2 sections, but you can do those on your own. And interrupt whenever you're ready or whenever you have a question. Some of the questions I'll answer that later, but feel free to ask me those questions. Any questions before we get started with I'm going to show you stuff. Okay, so an object in Python. Everything in Python at runtime is an object, absolutely everything. The creation of object is not related to names at all. Objects don't even know their names, and there are lots of ways to change namespaces. So first, let's just pretend I'm teaching my grade 4 child, which I do 2 years ago, a little bit of Python. Say, here's, well, no. My point is I'm going to slow down. Like I said earlier, I'm going to slow down really slow, and it's going to sound like I think you're stupid. I know you're not stupid. You're all very smart, but you may be thinking about this slightly differently. So when I type the 1 at the REPL, the read eval print loop, the interactive prompt, or in this Jupyter notebook, when I enter the 1 and hit shift enter is the way Jupyter works, Python sees the literal, the single character 1, the digit 1. It says, I know what to do with that. That's a literal int. I can turn it into an integer object. So it goes off and creates an object in memory, and that object takes a lot more than 32 or 64 bits. It's a very large object, and somewhere in there is a representation of the number 1. It then takes that object, and because it's being entered at the prompt, it's going to try to output a string representation, a character representation of that object, and so it calls dunder str and gets the character 1 back and prints it out on the output. Okay, I promise I won't do that the whole 3 hours, but that's exactly what happens, and I'm going to do it at least 3 or 4 more times. So I can create a number 1, I can create a floating point number, I can create a string. Each of these, whenever this happens, I'm going off and creating objects. Here, I actually created a 1 object, created a 2 object, created a list object, had the list refer to those things, and then the string representation came back out. So all that's going on every time Python executes a line of code. And I can, of course, do a dictionary. Every object has a single unique ID. All right. So the unique ID of the object that I'm going to create here is that. In CPython, this happens to be, at least currently, a memory address, and that's useful for people who are writing extensions. It's not guaranteed in all versions of Python to be a memory address, and I think in some it's not. What is guaranteed is it's unique. And there's another one, and there's another one. So I can take any of these objects I created before, I can ask Python, what's the unique ID of these things? Every object has some number of attributes. The way you access attributes, of course, is with dot notation. So I can look at that. I get kind of an awkward representation of what it is. It says pardon? Close enough. Okay. Well, welcome to the Python Epiphanies tutorial that I'll be teaching today. The link to the Jupyter notebooks that I'll be using, as well as some HTML files are there, is at bit.ly/PyCon 2017-Epiphanies. You're welcome to use those notebooks and follow along. There's a single notebook that has the word all in it. That's a compilation of all of the others except the intro, which might make your laptop unhappy because it uses lots of memory. And you're welcome to just look at the HTML as we go along, or just watch the screen and then use whatever other version of Python or means of typing stuff into Python to do exercises or try things out. Contact information is there. You can see here I've quoted from the description in terms of what sort of the not very precise in terms of facts, but maybe emotions in terms of where you might be, or the kind of people I'm really trying to serve well with this tutorial. People who've been using it for a while and maybe have plateaued, and this is to help you get beyond that plateau. I developed this tutorial after teaching other tutorials for a while, and sort of felt like there was this group of people that had been using Python for a while, especially if they'd come from certain other languages and just weren't getting certain stuff. Let's see, about me, I'm a software architect at a couple mutual fund companies in Canada. Most of my time I spend helping quants write Python. They're using pandas and Python and lots of math, some of which I understand. Some of this material is in a Python Epiphanies video at O'Reilly. This is a slightly rearranged and better version of it, I think. I've taught a number of Python workshops, tutorials at previous PyCons and other conferences. This is my 10th anniversary of teaching a tutorial at PyCon. So that's kind of exciting. And then I do coaching at startups as well on the side some. I asked you before we started recording some of these questions. What programming languages did you learn first? And I heard C and C++ and Pascal and Java and JavaScript, and some of you first language was Python. And I think a good mix of people in the room who've used Python from 3 to 8 years. And some of those other languages had used for a number of years as well. So in terms of how this is going to work, the first 5 to 8 minutes is going to feel like a dry, boring lecture, but I want you to try to pay attention because it sort of sets the groundwork for some of the other stuff. And then the first 10 to 15 minutes after that is going to, for some of you, feel really, really slow. Please don't leave yet. It's going to speed up and get better, but I want to sort of dumb things down a little bit for the first while to try to reset the way you think about certain aspects of Python. And I think by doing that, it will help you, even if you already know it in your head, it'll help you sort of get in the right frame of mind to understand Python and how it works and not be confused by it as often. So let me talk about variables. So a variable in math is something that varies, and we are used to this from algebra. Most programming languages, books, courses, culture, really give you, even if this isn't what you learned originally, you sort of absorb this understanding of what variables are in programming languages. Traditionally, the compiler reserves memory for a variable, and it issues type-specific instructions that depend on the type of what's going to be stored in that location in memory. When you make an assignment statement, it actually takes what's in that box and overwrites it with a new value, right? So if there was a 2 there, if I equals 2, and then you say, well, I is now assigned 3, the 3 overwrites. The bits in that box get overwritten with a 3 instead of the 2. Aliases are fairly rare, except maybe as function arguments passed in. Python is sort of on the spectrum of languages. It's toward the side that doesn't do that. It shares the math definition, which is a variable is something whose value varies, but only at a certain level of abstraction. This is unlike the traditional definition. And to avoid baggage, I'm going to use the words name. I'm going to use names and objects and binds and refers to, and I'm going to try most of the time